Hello and welcome to Sleepy Science. Tonight we'll loosen our grip on the obvious and drift through 30 gentle surprises. Speckles that follow your gaze, darkness coaxed from stacked polarizers, a slinky slowed until its hidden still points appear, and heat that quietly writes maps. We'll raise velvet spikes in ferrofluid, let water skate on its own vapor, then chill a drop so far past comfort it freezes at a tap. Sound will paint geometry. Kitchen fluids will harden when hurried. A toy diver will sink on command. Pepper will flee from soap, and a steel paperclip will rest on liquid skin. Glass will vanish in matching oil. White will split into rainbows by disc and window. Raisins will ride bubble ladders. A bottle will spin itself into a tidy tornado. A loop of wire will become a motor, and fruit will light an LED. Static will race a can. Copper will slow a falling magnet. Air will crush a cooled can, and a quick sigh will bloom a cloud. Colors will climb paper. Black will confess its choir. Cabbage will paint acids and bases. Cornstarch will grow standing shapes. Sand will braid two tempos. Eggs will reveal inertia, and forks will balance on a toothpick's tip. If this kind of quiet clarity helps you rest, settle in, breathe once, and let's begin. Laser speckle. Moving patterns that track your eye. Watch a rough wall under a quiet red laser and something unsettling happens. The sprinkled dots don't just shine, they seem to breathe, slide and follow your gaze as if the surface were alive. And that eerie glide is your first clue that perception trails reality by a few precious milliseconds, meaning the now you trust is already a little late. You're looking at laser speckle, a grainy pattern born when countless tiny reflections from microscopic bumps on the wall travel slightly different distances before reaching your eye. Some of those ripples of light arrive in step and add. Others arrive out of step and cancel. And the result is a frozen-looking map of bright and dark that, oddly, refuses to stay put when you move your eyes. The reason isn't magic in the paint, but mechanics in you. The pattern that forms on your retina depends on angles measured from your pupil. So when your eyeball shifts, through deliberate gaze or tiny microsaccades, the sampling changes and the entire twinkling landscape appears to slide. If the wall moves and you keep your eyes fixed, the speckle drifts one way. If your eyes move across a still wall, it drifts the other. Proof that the motion you feel can be an echo of your own action rather than the world's. Add to that a second truth your brain would rather hide. Sight arrives late. Photoreceptors take time to respond, signals crawl along nerves, and your brain spends a slice of a second cleaning, stitching, and predicting before handing you a scene that feels immediate. By the time you notice the grains slipping, they've already shifted, and your brain has already corrected for some of that shift with clever guesses shaped by experience. If this sounds abstract, you can make it personal in a minute. Tape a scrap of matte paper to a wall, dim the room, and gently sweep a safe, low-power laser pointer across it. Stand still, lock your head, and move only your eyes side to side. The speckle should appear to creep opposite your eye movement, like a star field refusing to stay where you left it. Now move your head with your eyes still fixed, and feel the direction flip. Squint a little and watch the grain size change. A smaller pupil blurs fine structure, and makes the bright and dark patches look larger, because your aperture, the opening that admits light, sets the resolution with which you sample the interference. Step closer and the speckles swell. Back away and they shrink. You are not merely a spectator but part of the instrument, and the instrument controls the show. The reason it works best with a laser rather than a flashlight is coherence. Laser light has waves with nearly the same color and phase marching together, so the interference stays sharp across the field, while ordinary white light is a riot of mismatched colors and phases that wash the pattern out before you can notice it. Speckle gets even more intriguing when you look at living tissue, because the pattern is exquisitely sensitive to motion, vibrating membranes, flowing blood, or even the gentle tremor of your own body can make it flicker and smear. And that is why researchers can use speckle contrast as a window into flow without ever touching a vessel. Movement turns the crisp static map into a soft blur whose texture tells a story about speed. None of this requires equations to feel true. You can sense it in your body. Try briefly staring at the speckles and then closing your eyes. You'll notice a ghost pattern that fades as photoreceptors recover, a reminder that your retina has its own memory. Notice too how your brain stabilizes the world during eye flicks. Each micro movement should drag the speckle, yet you don't perceive a jerky universe because your brain edits and anticipates, eliminating what it expects to be self-generated motion so you can track objects smoothly. That editorial instinct helps you survive, but can also mislead, because sometimes the brain subtracts too much, or adds confidence where there should be doubt. Speckle is a kind teacher here, offering a safe lens on the hidden machinery of seeing. And the lesson runs deeper. What you call out there is inseparable from the geometry of how you look, from the timing of your neurons, and from the assumptions your mind leans on to fill gaps. Laser speckle isn't an illusion in the sense of a trick. It's a revelation that measurement conditions, your pupil size, your position, your micro movements, the coherence of the source, co-author reality's appearance. That means your present is not a raw feed, but a carefully prepared dish served a heartbeat late. And once you notice that delay, other experiences quietly fall into place. Why fast-moving objects smear across your awareness before they resolve. Why a sudden sound seems to tug your eyes to where your brain predicts the source will be. Why under stress, you can misread a shifting shadow as motion that isn't there. You can refine the speckle experiment without fancy gear. Hold a sheet of clear plastic with a frosted patch. Let the laser splash on it and gently flex the plastic. Stress changes its microscopic roughness, and the grains shiver in response, turning force into a visible tremor. Or rest the beam on the back of your hand and notice how a single heartbeat can ripple the pattern. A pulse of life written in light. Along the way, respect safety. Never aim any laser at eyes. Use low power. Avoid mirrors. And respect what the effect is really telling you. There is no single picture of the world, only pictures produced by ways of looking. And the timing of those pictures is always just behind the event. In that sense, the moving speckle is less a curiosity and more a mirror. When it seems to follow you, it's revealing how much of your reality is assembled by your own motion, your own sampling, your own brain's gentle act of prediction. Perhaps that's the most practical lesson to take into the rest of your day. If even a painted wall can appear to flow because you shifted your gaze, then moments that feel fixed may be more negotiable than they seem. And habits of attention can change what you experience without the world changing at all. When you switch the laser off and the grains vanish, the room looks ordinary again. But you carry a new habit, checking how you're looking, not only what you're looking at. And that small pause is enough to turn perception from a reflex into a craft, so the late arriving present can feel less like a verdict and more like a choice. Polarizers, impossible darkness with 3 filters. Turn a thin square of polarizing film slowly in front of a bright, even light, and you can stage a quiet miracle on your desk. With 2 sheets crossed at right angles, the view collapses to velvet black. Yet when you slip a 3rd sheet between them and tilt it to a middle angle, light seeps back through as if darkness itself had been tricked. A result that feels impossible until you learn what these filters really do to the hidden orientation of light's vibrations. And that small shock of surprise is your doorway into a deeper habit of seeing, where you notice that what feels obvious often hides the simple, testable rule beneath it, and that your sense of now happily accepts a story your brain prepared a heartbeat late. A polarizer is not a color filter. It is more like a gate that only opens for waves vibrating in one preferred direction. And most everyday light is a jumble of directions at once, produced by countless emissions and reflections with no coordinated orientation. So the first sheet quietly selects one direction and throws away the rest. Look through it at a reflective glare on water or a car hood, and you see why anglers and drivers love polarized sunglasses. The shimmering blast is already lined up by the way light bounces off a surface, so the filter can suppress it and reveal details your eyes were missing. If you add a second polarizer in exactly the same direction, little changes, but twist that second sheet 90 degrees, and the gate you opened with the first is now blocked by the second, so the field turns dark. And that is the moment most people seal their intuition. One lets it through, the other cancels it. So 2 crossed sheets mean darkness, full stop. Then you add the third, positioned halfway between the other two, and the impossible happens. What was black becomes visible again, not because the middle sheet makes its own light, but because it gently swivels the orientation of what survives the first sheet into a new direction, where a fraction can also survive the last, like walking down a hallway with a series of doors that only open if you turn your shoulders each time. Individually, each door is strict, but a gradual sequence lets you pass. There is no special math you need to memorize to trust this. You can feel it in your hands with 3 cheap films and a lamp, and you can tune it like a dimmer by changing the middle angle. Near the first gate's direction, the scene brightens. Near the final gate's direction, it dims. And at exactly halfway, it becomes a quietly astonishing proof that intuition improves when you give it the right experiments to chew on. This isn't merely a parlor trick either. Whole technologies harness the same principle. Your phone's screen is a controlled light valve built from liquid crystals sandwiched between polarizers, and each pixel rotates the orientation of passing light by twisting its molecules under an electric field. So when the twist lines up with the second gate, the pixel glows, and when it doesn't, the pixel darkens. Rotate a polarizing film over your phone and you'll watch the image fade and reappear, not because the phone changes, but because your wandering gate now either cooperates with or fights the screen's built-in one. Take the exploration further with white light instead of a single color. Slide a piece of clear plastic, like a cheap ruler or the lid from a takeout container, between 2 crossed polarizers, and it suddenly blooms with tinted patterns, as if the material were stained glass. Those colors come from stress birefringence, a mouthful that just means the material delays one direction of vibration more than the perpendicular one. And that small mismatch depends on thickness and internal stress. So some colors end up rotated enough to pass the second gate while others are blocked, painting stress lines you can't normally see. If you want a gentler entry point, pour a glass of sugar water and slip it between crossed polarizers. Many sugars are optically active, which means the solution rotates the orientation of light slightly, and the amount of rotation grows with the path length and concentration. So you can watch brightness wax and wane as you change the glass or stir the mixture, the kind of kitchen physics that turns sweetness into a measuring tool. Step outside on a blue dry day and you'll meet another quiet ally. The sky itself carries a subtle polarization pattern because sunlight scatters from air molecules in a way that prefers certain orientations at certain angles from the sun. A rotating polarizer reveals that hidden map by letting you dim and brighten patches of sky without changing your position. And that trick, reading the sky's polarization, shows up in animal navigation and in photographic tricks to deepen blue and tame haze. Even reflections hold a secret gate. At one special glancing angle off glass or water, known to photographers as the sweet spot for glare control, reflected light is strongly polarized, which is why a small twist of polarized sunglasses can erase a window's harsh flare and show the scene behind it. If you find the 3 filter effect unsettling because it seems to violate 2 crossed means black, remember that nothing illegal happened. Each filter keeps only the component of the wave aligned with its own direction. And by inserting a middle step, you give the wave a chance to lean toward the final gate in stages. You haven't created energy, you've managed orientation. Real hardware makes the lesson friendlier still, because no polarizer is perfect. Films leak a tiny bit even in their black configuration, and the polymers that do the work, long chains stretched during manufacturing and often doped with iodine to create rows of tiny electron highways, have microscopic flaws. That's why your cross darkness is deep charcoal rather than infinite night, and why rotating away from perfect crossing gradually fills the view instead of switching it like a light. Build your own kit and you'll start noticing the world's hidden filters. The way a laptop screen nearly vanishes when you tilt your head because its polarizer conflicts with your glasses. The rainbow stress map trapped inside clear plastic spoons when you hold them against your phone. The rotating glare on a lake that bows to your sunglasses with a practiced nod. And you may notice a subtler rhythm too. As you turn the film in your fingers, the brightening and dimming feel smooth, not choppy, because your vision averages over brief flickers and your attention lags by just enough to make the change feel continuous. A gentle reminder that the story of what you see is assembled and delivered slightly after the world has already moved on. You are not being fooled, you are being helped to function. But the help comes with a cost. Certainty that arrives just late enough to make surprises feel personal. The best part is how empowering this is. You don't need lasers or symbols to test deep ideas. Only a few sheets of inexpensive film, a screen, a window, a bit of plastic, and curiosity. With those you can witness gates in light, rotations you can dial with your wrist, colors born from stress you couldn't guess by eye, and a darkness broken by adding more filters. Moment that flips common sense into informed sense. And maybe that's the real gift of the 3 polarizer trick. You walk in expecting more barriers to mean less passage. Then you discover that adding a carefully chosen middle step can open a path that brute force closes. And you carry that template beyond the desk. Sometimes the way through is not to push harder against the final gate, but to add a thoughtful turn in between. To change the orientation of your approach so what seemed impossible begins, quietly, to pass. Slinkies and slow motion, hidden standing waves. Pick up a slinky and give it a playful shake, and for a heartbeat it looks like chaos. Coils rippling, arcs leaping, a silver river that won't make up its mind. But the moment you nudge it in rhythm, a secret geometry begins to bloom. Bright, calm islands that barely move and swollen rivers that surge between them. A pattern that seems to hover in place, even while motion is everywhere. And slow motion on your phone finally lets you see what your eyes miss at full speed. Standing waves, the quiet architecture of vibration that hides inside almost anything that can wobble. You don't need formulas to make this appear. You need a stable endpoint, a steady hand, and patience. Tape one end of the slinky to a smooth wall or a heavy chair leg so that end cannot wander. Then hold the other end waist high and give it gentle side-to-side nudges at a relaxed, steady tempo. At most speeds, you'll get messy traveling ripples, but at a few special tempos, where the timing of your hand's push matches the time a pulse needs to go down and back, the mess locks into a shape that looks eerily still, places along the spring that barely budge and bulging sections where motion concentrates. It is tempting to think the spring has stopped, but slow it down on video and you'll notice the truth. The shape is steady, while material is not. The coils in each bulge race back and forth through that region, while the nodes are where equal and opposite motions cancel, like cars flowing through a city whose skyline doesn't change. If you want a friendly recipe, use a metronome app or a drum loop and sweep your hand speed from slow to quicker in smooth steps. You'll feel clicks where the pattern catches and becomes clean with one bulge, then 2, then 3. Each one a higher mode that needs faster driving. These modes are like rungs on a ladder. The lowest one spans the whole length with a single fat rise in the middle. The next shows 2 rises separated by a still point. The next shows 3, and so on. And the more rungs you climb, the more sensitive the pattern becomes to where you hold the slinky and how steady your timing is. Change the length by walking closer to the wall and the favorite tempos drop. Step back to lengthen the spring and those good tempos. Rise. Longer springs prefer slower rhythms and shorter. Springs like quicker ones because the pulse has less distance to travel before it returns and either helps you or fights you. Change the tension by pulling a little tighter, and you'll also change the comfort zones. Higher tension makes the pulse zip faster, shifting which hand speeds lock in while a slack, droopy spring damps the motion and blurs the sweet spots into mush. If you're curious about the ends, switch the boundary and watch the pattern respond. The taped end behaves like a fixed point where motion must vanish, so a node lives there. If instead you hold both ends lightly and let the spring slide on a slick surface, the ends can act more like free points, and the pattern adjusts so motion peaks near them. In both cases, the whole shape is disciplined by what the ends allow. There's a deeper lesson inside this play. What looks still can hide flow. Energy ripples through the slinky, reflecting from the ends and meeting itself on the way back. And at certain rhythms, the meetings are friendly. Returning motion adds to the next push you give, reinforcing the bulges. At other rhythms, the return arrives out of step and ruins your effort, and the shape collapses into noise. This cooperation is what people mean by resonance. not a mystical buzzword, but a practical agreement between timing and structure. Because a slinky is a helical spring, it can host more than one kind of wave. When you shake it sideways, you send a sideways wiggle. When you compress and release along its length, you send a compression ripple. Both can make standing waves, though the side-to-side version is easier to see, and both are slowed and softened by friction and internal rubbing, which is why real patterns take a moment to settle and a moment to fade. To make the hidden order visible, add a few low-tech tricks. Slip small paper flags onto a handful of coils so you can track motions at different positions. Dust the spring lightly with flour to trace blur widths on video, or run the slinky on a dark table with a single desk lamp to cast sharp shadows that outline the nodes. You'll notice that as you climb to higher modes, the bulges become closer together and lose endurance. The system leaks energy faster at finer scales, so your hand must become more precise to keep the structure alive. That is why orchestras love low notes for their warmth and weight, while high harmonics sparkle briefly and vanish. This little desk experiment also explains instruments and machines you know. A guitar string shows standing waves when you touch it at the halfway point to make a harmonic. The place you touch becomes a node, and the string chooses a shape that honors it. A room with poor acoustics can trap certain tones because the walls impose fixed or nearly fixed ends, letting some frequencies swell while others die. A poorly designed bridge or sign can wobble itself into trouble if wind or periodic traffic happens to match one of its favored shapes and feeds it energy every cycle. Engineers work hard to move those favorite tempos away from what nature provides, and to add damping so a bridge forgets any rhythm it picks up before it becomes dangerous. Back at your desk, you'll quickly discover that your own timing is the whole game. If your hand arrives a little early each cycle, you'll push while the returning motion is still coming the other way, and the bulges will starve. If you arrive just late, you'll always give a boost as the spring passes through neutral and wants to continue, and the bulges strengthen and clarify. That phase relationship, the alignment between your push and the system's swing, is why a gentle, well-timed nudge can do what a hard, clumsy shove cannot. And once you feel it in your wrist, you'll start noticing it in daily life. The perfect moment to rock a stuck drawer free, the rhythm that makes a child's swing climb with hardly any effort, the way a crowd's chant can synchronize and swell until the air shakes. None of this asks you to believe beyond what you can test. Try holding the slinky a little off the table so it can move freely and switch your drive from side to side to up and down. You'll seed a different family of patterns because gravity now biases the motion and the coil spacing is no longer uniform. Try starting with a single, sharp pulse instead of a steady rhythm. Pinch and release quickly to launch a hump that runs down, reflects, and, when the timing is right, helps build the standing shape after a few bounces. In slow motion, you will see the humps approach, overlap, and, for an instant, create a higher bulge before separating. A handshake that leaves the skyline unchanged, but moves energy onward. Try lightly touching the slinky at a point that isn't supposed to move in your current mode. The standing wave will survive because you've chosen a node, but touch where a bulge lives and you'll ruin it. The fastest way to learn that structure is not decoration, but instruction. If you want a thought to carry out of the room, let it be this: structure and timing govern what persists. The slinky shows you that a system will happily organize into clarity when you feed it energy at the right moments and starve it of friction. And it will just as happily dissolve into noise when your help is out of step. That is not merely a rule for springs. It is advice for skills, habits, and attention. When you stop, the last bright bulge sighs away into small ripples and then into stillness. And the table returns to being a table, but you felt something you can't unfeel. Order is available, often nearby, if you learn the few rhythms a thing prefers and meet it there with patience. Thermochromic maps. Heat as an invisible pen. Lay a sheet of thermochromic film on your table and press your palm flat against it, and you'll feel almost nothing happen while your eyes watch everything change. Your hand lifts, and a glowing imprint lingers like a quiet secret. Fingers and whirls and the soft heel under your thumb. A map made not of ink but of temperature. proving that heat can write where ordinary pens fail, and that everyday touch leaves traces you rarely notice until you give it a surface that can confess. This is the charm of thermochromic mapping. You borrow a material that changes color with temperature and use it to make invisible flows visible, turning the gentle physics of warm to cool into an instant picture you can read. The film looks plain at first, usually dark, sometimes a dull green or blue, but it's engineered with microcapsules that hold dyes in two states. At lower temperatures, the molecules settle into a form that absorbs certain colors and looks inked, and when warmed, they rearrange into a different form that reflects more light and seems to erase, so a warm touch becomes a bright print, while a chilled coin draws a dark line across the glow. In other versions, liquid crystals do the trick, twisting with temperature and selectively reflecting different wavelengths, giving you a rainbow that slides from red to blue as the surface warms, a mood ring effect you can sculpt with breath, ice, and sunlight. If you want to teach your eyes how heat actually travels, start with contact, the simplest pathway. Place a metal spoon and a wooden spoon side by side on the film and touch both for the same time with the same hand. When you lift them, the metal side shows a larger, brighter patch even though you pressed no harder, because metal conducts heat much more efficiently than wood, drawing warmth from your skin fast and spreading it swiftly under the surface. So the film reaches its color change threshold over a wider area. You learn at a glance that materials differ, not just by feel, but by how quickly they share thermal energy. Swap the spoons for a coin, a ceramic cup, and a folded paper towel, and you'll see three distinct signatures. The coin makes a crisp-edged, high-contrast stamp. The ceramic smudges slowly outward, its heat capacity acting like a reservoir that sips rather than gulps. The paper barely leaves anything at first, but insulates what sits above it, so if you rest your forearm on the paper over the film, the print that emerges is faint and late, a delayed echo shaped more by trapped warmth than by direct contact. Same hand, different story, because pathways can help or hinder. Now move to air, the second great messenger of heat. Set a small desk fan to low and blow across the sheet after warming it with your palm. You'll watch lanes of cooling sweep from the fan's center outward like river deltas, thinning as they spread, and where the table edge meets the film, the pattern sharpens, because edges are where heat escapes fastest, giving your map natural borders. Stop the fan and watch the colors drift back as the material relaxes toward room temperature. A reminder that what you drew wasn't permanent. It was a snapshot of a process trying to balance. Try breath next. Fog a gentle stream across the film, and you'll create a soft, mottled bloom shaped by tiny turbulence. Cup your hands and exhale through the gap to focus a warmer plume, and a brighter oval appears with feathered edges that tell you how unsteady your stream really is. A hairdryer on the coolest setting, held far away, makes wider, steadier gradients you can stencil through a piece of cardboard, letting you spray paint with warmth and watch the pattern vanish in reverse as the heat drains away. Radiation is quieter, but real. Park a dark mug filled with hot water on the film without touching. If the gap is tiny, you'll still coax a faint halo underneath over a minute or two, because infrared from the mug warms the air and the surface below. Swap in a shiny metal mug and the halo shrinks. Not because the mug is colder, but because shiny surfaces radiate less efficiently, so less energy drifts downward. A small lesson in how color and finish change thermal stories even when temperatures match. Once your room becomes a lab, you can time the fade and pull meaning from it. Press your index finger for 2 seconds. Lift and count how long it takes the print to return to baseline. Press for 6 seconds. Lift and count again. The second mark lingers longer because you delivered more energy. And the fade time depends on the film's thickness, the table's ability to carry heat away, and the air's motion. Turn the fan back on and the ghost collapses quickly. Slide a magazine under half the film, and the prints on that half persist because you've added a thermal blanket that slows the leak. Try a little cartography. Draw a rough grid with painter's tape on the film and warm the surface evenly with your flat palm. Peel the tape and you'll reveal cool, sharp lines. Tape blocked heat from reaching those lanes. So your map now carries crisp streets across a brighter city. Brush your wristwatch across the warm field, and its metal back will carve a distinct dark line. But the band leaves a paler path, a contrast born from differences in conduction and contact. Tape a leaf to the film, warm the whole area with diffuse breath, then remove the leaf and admire the silhouette. Its veins light up where the film warmed more through the gaps. A pocket-sized demo of micropatterns controlling the large picture. If you want something that challenges your intuition, touch the film lightly with a cold fork and remove it quickly. Then touch the same spot with your warmer fingertip, and you might see a dark fork print flare darker for a moment before fading as the finger presses. Why darker? Because you briefly improved contact and pushed the coal deeper, making the local temperature dip before it rebounds. What looks like a simple stamp is a layered dance of contact, pressure, and time. With a liquid crystal sheet, the lessons expand in color. Slide a chilled marble across a warm patch and watch a bruise of deep blue track behind it. Then lift the marble and see the tail smear toward green as the film recovers. Rest a plastic ruler on the sheet and flex. A rainbow band rides the stressed edge because the film is thin and the pressure changes how it conducts and releases heat. Pass a finger slowly and a red-gold arc flows in your wake. Go too fast and nothing appears because the die needs a beat to rearrange. Your map is not just about where heat goes, but about the tempo it needs to leave a record. Safety is simple. Keep temperatures moderate. Warm hands, warm cups, cool coins, gentle fans, hair dryers on low from a distance. Avoid direct contact with very hot surfaces. Keep liquids sealed or wiped to protect the sheet. And remember that these films have a working range, usually just a dozen degrees around room temperature, so if your studio is too cold or hot, you'll shift the palette and may need to adjust your expectations. The most practical gift of these maps is that they teach you to look for asymmetry. Why does the edge cool first? Why does a corner wick warmth away faster than the center? Why does a tiny draft carve a canyon in one direction but not the other? Answers arrive without equations. When you notice that heat always seeks balance, prefers short, easy paths, and broadcasts its journey in gradients rather than hard borders. And a softer lesson hides underneath the color. The traces fade. But while they're alive, they tell you where connection happened, how long it lasted, and how strong it was. Touch becomes visible. Rest leaves a signature, Motion writes in cursive. When the sheet goes blank again, nothing has been lost. Only the balance has returned. Close your session by warming the whole film with your palms until it glows. Then lift and watch the brightness fall evenly back to uniform. The way a crowded thought settles when you stop feeding it. You don't need special symbols to leave with real knowledge. Only a square of film, a few objects, and the patience to read what the colors are saying. That heat is a gentle author. Contact is a sentence, air is punctuation. And time is the eraser that brings everything back to calm. Ferrofluids, field lines you can see. Set a glossy black drop beneath a strong magnet and watch it grow a forest of needles that shiver and hold like a creature bristling. This is ferrofluid, a liquid that behaves like ink with the instincts of iron. And for once, you don't have to imagine invisible magnetic fields, because the shapes they prefer stand up in front of you. Sculpted by forces you can steer with your hand, it feels like a magic trick until you learn what's inside the bottle. Countless iron oxide nanoparticles, each tiny enough to rattle with thermal motion, each coated with a surfactant so they don't clump, all floating in a carrier oil that lets them slide past one another like a crowd in a dark room that suddenly obeys a quiet signal. Bring a magnet close, and those particles line up along the field, not as a solid bar, but as flexible chains that tug on the liquid around them. At first, surface tension resists, smoothing the droplet into a dome. But as the field grows stronger, a new shape wins, a spiky array of peaks and valleys that lowers the system's energy by letting more magnetic threads reach outward while keeping the volume roughly the same. That tipping point, where smoothness gives way to spikes, is a hallmark of this material and goes by a sober lab name. Yet you can feel it with your fingers. Drift the magnet closer, and the surface suddenly stipples into an armored bloom. Pull away, and the forest sinks back. the liquid relaxing as if exhaling. You can try this safely at home if you respect two rules: containment and distance. Pour a small puddle of ferrofluid into a shallow petri dish. Then place a thin glass sheet, like a microscope slide, on top so the fluid can't leap toward the magnet and stain your workspace. Hold a strong neodymium magnet under the dish and move it in slow circles. The spikes orbit like a crown, always pointing toward the magnet's heart. Flip the magnet and the symmetry changes. Slide in a stack of paper between magnet and dish, and the spikes soften, because field strength drops with distance, and the forest thins when the tug weakens. Now try different magnet shapes. A ring magnet pulls the fluid into a donut with an inner moat. A bar magnet draws a field that stretches the spikes into aligned ridges. An array of small cube magnets set side by side creates a chessboard where peaks arrange in tidy grids. Wherever the field changes fast, spikes crowd close, revealing gradients your eyes could never see without this living indicator. What makes ferrofluid special isn't that it contains magnetic stuff. Lots of materials do. But that the particles are so small, they don't hold a lasting magnetization once the field is gone. They behave like tiny compass needles that flip freely under thermal jostling, aligning instantly when encouraged, relaxing when released. So the liquid never becomes a permanent magnet in your drawer, and you can perform the dance again and again without a lingering imprint. Temperature and viscosity matter. A cooler, thicker fluid responds more slowly but holds sharper, steadier spikes. A warmer, thinner brew flows eagerly but blurs the details. Shake the dish and you'll see the fluid's loyalty tested. Too much motion and the spikes melt into waves. Too little and they freeze into statues. Change the distance by a millimeter and the skyline of peaks redraws itself. A live graph of force you control with your wrist. Those glossy needles have consequences beyond spectacle. Engineers trap ferrofluids in the tiny gap between a spinning shaft and a fixed housing, then hold them in place with ring magnets to create seals that are both tight and frictionless. Perfect for vacuum systems and spinning glass on telescopes. Audio designers fill a narrow ring around a speaker's voice coil with ferrofluid because it wicks heat away as if the coil had a private river, allowing louder sound without damage and quietly damping harsh resonances. Medical researchers experiment with targeting, hoping to steer drug-laden particles with magnets to where they're needed most. Artists and educators use the mesmerizing bloom of spikes to teach how fields shape matter without touching it. To see more nuance, add a few simple props. Sprinkle a dusting of fine glitter atop the glass cover. As you move the magnet, the glitter lines up along the hidden ragged edges of the peaks. A second layer of field lines that you can brush off afterward. Place a thin steel paperclip on top of the glass and bring the magnet closer until the clip just begins to feel tugged. Watch how the spikes reach for it, even though the fluid never touches metal, because the field now threads through the clip as well, reshaping the landscape in the dish. Try sliding a scrap of aluminum between magnet and dish, and notice how little changes. Aluminum doesn't strongly redirect the field. Then repeat with a soft iron washer and see the spikes reorganize instantly. Proof that some materials offer the field a more comfortable path. Keep your setup gentle. Neodymium magnets are unforgiving, pinch hazards for fingers and traps for credit cards, and ferrofluid loves to stain. So gloves, glass barriers, and a dedicated tray are your friends. Do not put magnets near watches, hard drives, or medical implants, and keep the bottle capped when not in use to prevent the carrier oil from thickening over time. If you listen closely to what this liquid teaches, you learn how competing wants decide a shape. Surface tension wants smoothness to minimize area. Gravity wants flatness. Magnetic energy wants tall spines that offer more alignment. Viscosity wants slowness. The winner is the compromise you can see. Tilt the dish and the peaks lean like trees in a steady wind. Keep the magnets still and the fluid slowly creeps downward while the spikes remain, telling you that flow and structure can diverge. What looks solid is sometimes a pattern maintained by forces, not by fixed parts. And there's a gentler lesson wrapped around the science. Ferrofluid makes the invisible not just visible, but negotiable. When you move the magnet a little differently, the entire pattern responds, which suggests a habit of mind you can carry outward. Fields you don't notice still shape outcomes, and small, steady adjustments can reorganize a whole scene without violence. End your session by easing the magnet away until the needles sigh back into a black mirror. What remains is a pool so calm it denies what you just saw, yet with a single motion you could raise the forest again. That's the quiet beauty of this demonstration. It's honest, it's simple, and it leaves you with a permanent upgrade in intuition about how forces compete, how structure emerges, and how a hidden order can wait inside apparent stillness, ready to stand up the moment you give it the right pull. Leidenfrost effect. Water that hovers and skates. Slide a single drop of water onto a pan that's truly, dangerously hot, and it behaves like it forgot what water is. No frantic fizz, no quick vanish, but a silvery bead that hovers on a whisper of its own vapor and skates away like a tiny puck, zigzagging around bumps and outrunning your attempts to trap it. That first wrong-looking glide is your doorway into the Leidenfrost effect, a regime where temperature flips ordinary boiling into a new game and teaches you that the path to faster isn't always more contact, but sometimes less. You can explore it with kitchen tools if you're careful. Set a dry, clean stainless steel pan on medium heat for a while. Keep your face well back and flick in a few tiny drops from your fingertips or a straw. At low heat, they spread into dull puddles and slowly steam away. Routine evaporation. As the pan climbs closer to a vigorous simmer, the drops explode into lively bubbles that rattle and spit. Nucleate boiling, where microscopic pockets of vapor form at rough spots and burst. Then, if you continue heating into the territory well above water's usual boiling point, something strange happens. Fresh drops don't grab the surface at all, but shrink into hard pearls that hiss faintly and scurry with almost no friction, lasting far longer than they do at lower temperatures, because a thin cushion of vapor now separates them from the pan like an invisible air bearing. That cushion is self-made. The part of the droplet nearest the metal flash evaporates, building a trapped layer of gas that insulates the rest of the liquid. So heat flows in more slowly than your instincts predict, and the bead survives, moving on a mattress of its own making that is constantly renewed at the bottom and vented around the edges. Material and finish matter. A heavy cast iron skillet tends to reach the effect later than a thin aluminum pan because of how it stores and spreads heat. Rougher surfaces seed ordinary boiling at lower temperatures and can resist a stable hover until you push the heat higher. Add a thin film of cooking oil and you've changed the terrain again, often delaying the hover because oil alters contact and vapor escape routes. If you want a gentler probe, heat a stainless spoon by dipping it repeatedly into boiling water or by resting it over steam, and then touch a tiny drop to the underside. If the bowl is hot enough, you'll see the drop skitter instead of sticking. A pocket-sized demo you can do at arm's length. The life of that bead is a miniature story in stages. At first it circles the hot zone, driven by tiny imbalances in how vapor escapes left versus right. If the surface has a slope, the drop may climb uphill, propelled by vapor that prefers to push from the warmer side, like a hovercraft that keeps turning toward the strongest breeze. If the underside of your pan isn't uniform, the droplet will drift toward cooler patches that feed it vapor more gently and let it persist. Tilt the pan slightly and you'll see controlled skating. Hold it level, and the paths become a wandering blueprint of the heat map you can't otherwise see. In slow motion, a big bead can pulse in and out, flattening and rounding like a living heart. Those are shape oscillations driven by the tug-of-war between surface tension, trying to keep the droplet spherical, and vapor pressure pushing up from below. At certain sizes, the bead sprouts crisp lobes around its rim, becoming a star that rotates as it slides, a playful pattern born from coherent ripples marching around the edge. If your pan sings a faint high note while the drop darts, you're hearing the bead's vibrations modulate the escaping vapor, sound carried by steam. Counterintuitively, a hover drop almost always lasts longer than a same-size drop on a merely hot surface. Not because the metal is kinder, but because the insulating layer throttles the heat transfer. That's why cooks use mercury balls of water to test if a pan is ready for searing. You're in the hover regime when the beads zip and dance, and you have the browning power you want without water gluing food down. The effect isn't a water-only club. Liquid nitrogen on a room temperature table shows a dramatic, safe-to-watch version because its boiling point is so low. The warm table is effectively red hot to the nitrogen, and droplets roll freely across the bench on cushions of their own cold vapor, billowing fog like stage smoke as they go. In lab videos, you'll see nitrogen, beads racing through mazes and climbing steps carved, with tiny sawtooth grooves called ratchets, microscopic, ramps that direct vapor flow in a preferred direction so the beads self-propel like smart marbles. You can't do that with kitchen water safely, but it tells you a deeper truth. Engineered textures steer the hover. Researchers engrave plates with herringbone, chevron, or ratchet patterns and find that the droplets reliably cruise along chosen paths, making contact-free transport possible in places where contamination must be avoided. Even without fancy textures, a simple notch or ridge in the pan will guide the drop because the vapor layer is thinner where escape is easiest, and thinner means more push on one side than the other. If all of this seems to contradict the common sense idea that hotter always means quicker evaporation, hold both thoughts at once. Just above boiling, water hugs the metal, exchanges heat aggressively and vanishes fast. Far above boiling, the droplet levitates, exchanges heat reluctantly through its vapor blanket, and lingers, skating as it shrinks. The boundary between those regimes has a name among heat transfer engineers, the point where film boiling begins, and its exact temperature depends on material, roughness, and what liquid you use. You don't need the number to learn the lesson, only your eyes and a respect for how radically behavior can switch when conditions cross a threshold. Safety deserves its own paragraph inside your mind. Do not crowd your pan with water when it's smoking hot. Keep splashes tiny. Wear eye protection if you have it. Keep your fingers well away from the metal. Turn handles inward and work with ventilation. If you use a spoon, heat it patiently with steam rather than a direct flame. Test with one drop and let it cool before handling fully. Never chase beads with your hand, and remember that the same insulating vapor that protects a droplet does not protect your skin. Touch the pan and the cushion is gone. Lessons you can carry beyond the stove arrive quietly as the pan cools and the skate stops. As temperature falls back through the threshold, the same droplet behavior rewinds. Hover becomes sputter. Sputter becomes a steady puddle, and the bead finally sticks and steams, teaching you that many systems have switching points where the rules change, and that pushing harder across such points can be worse than adjusting your approach. In messy real life, that might mean easing contact to glide rather than gripping and grinding. In design, it might mean texturing a surface to guide motion without a motor. In thinking, it might mean recognizing when an old habit of more force has carried you past the sweet spot into a regime where you're insulated from the result you want. When you finally turn off the flame and the pan sighs back toward room temperature, the last hover bead disappears and the metal looks just like any other Tuesday. But your sense of what heat can do is not quite the same. You've seen a liquid invent a cushion on the fly. You've watched shape become a vehicle. You've felt how thresholds split behavior into different worlds. And that knowledge lingers, like the faint ring a bead leaves in your memory, ready to remind you that sometimes the surest way forward is not to press down harder, but to learn how to ride the thin layer that makes motion possible. Supercooled water, a liquid that freezes on command. Set a clear plastic bottle on the counter and imagine this. It has been sitting quietly in your freezer for a couple of hours. Not rock hard, not fully liquid either, just resting in a delicate state you can't see. Then you loosen the cap, tip the first drop onto an ice cube in a bowl, and a white vein races up the stream into the bottle, turning the whole thing solid before your breath catches. It feels like a magic switch. But what you've made is supercooled water, a liquid chilled below its normal freezing point, that stays liquid until you give it a reason to become ice. And that reason can be as gentle as a tap, a tiny crystal, or a scratch on a surface. Water doesn't freeze just because it's cold enough. It freezes because an ordered starting patch forms and grows, and that first patch, called a seed, has a cost. Molecules must line up and lock together, and in a perfectly smooth, pure, undisturbed sample, that first step is oddly difficult. So the liquid can slip under the usual line where you expect ice, sitting in a quiet, temporary balance that ends the moment you introduce a cue. You can coax this at home with care and patience. Choose unopened bottles of clean, low mineral water in flexible plastic. Place them on their sides in the coldest, still corner of your freezer where they won't be jostled, and check them after about 2 hours by peeking through the door without moving anything. Timing varies with freezers, so the experiment is more listening than clockwork. When the bottle looks fully liquid but a little thick, lift it gently, crack the cap open to release any slight pressure, and pour onto a single ice crystal sitting on a spoon or into a chilled glass. And watch liquid turn to slush in a rising wave, as if you had pressed a hidden button. The trigger can be different. A sharp tap on the counter sends a pressure wave through the bottle that helps molecules line up. A grain of ice or even a dusty scratch offers a ready-made template where the first layer of the crystal can begin. A rapid pressure drop when you uncap can tip the balance too. If you film the moment closely, you'll see a white front bloom and race because the first formation of ice releases heat. Freezing gives back energy even as the environment stays cold. So the front carries its own tiny warmth and stabilizes the crystal shape as it advances. A traveling decision that leaves no ambiguity behind it. The reason purity matters is that everyday water carries microseeds, mineral bits, microscopic fibers, tiny bubbles, rough container walls, even vibrations from footsteps in the kitchen. Each of these offers a foothold for order. So water in an ice tray rarely supercools because the tray is full of edges and dust and motion. Sealed, smooth bottles work better because the liquid has fewer places to begin freezing and because the thin plastic absorbs small impacts rather than passing them along. If you want to explore the boundaries, try 3 bottles at once. Distilled water in one, filtered tap water in the second, and sparkling water in the third. Chill them together and notice how the sparkler misbehaves. Dissolved gas makes bubbles that serve as eager seeds, so it tends to freeze first when disturbed and may erupt into slush the instant you pop the cap. The distilled bottle is your star, often staying liquid the longest and freezing most dramatically on cue. The filtered tap bottle lands between them, teaching you that water is a story of context rather than a single rule. You can also paint with the effect. Set a shallow metal pan on an ice pack until it is deeply chilled, then pour supercooled water into it and watch the liquid creep across the frosty surface and lock into a glassy sheet behind a moving edge. If you dust the pan with a sprinkle of salt in one corner, the front will hesitate there because salt fights crystal order and lowers the point where freezing can grow. So the icy skin develops shape as it avoids that region, a landscape laid down by chemistry you can see. On a very still winter day, you may have met supercooling outdoors without knowing its name. Freezing rain is supercooled water in the sky, liquid droplets below the usual freezing point that remain liquid until they touch a branch, a wire, or a car, and then flash into ice on contact. Sheathing everything in glass, beautiful, dangerous, and a reminder that a system can carry hidden tension that releases on touch. In your bottle, that release comes with a second surprise. Once the wave has run, the surface warms slightly, and a bloom of mist can rise from the new ice because the heat given off by freezing makes the air above it carry a little more vapor. You can see and feel the rebalancing. The shapes you grow also hold lessons. Sometimes the bottle fills with a cloudy mass of tiny crystals because many seeds started at once, a flurry of beginnings overwhelming any single direction. Sometimes a blade shoots from the bottom and branches with delicate side growth, each arm following how water molecules prefer to arrange themselves in hexagonal order. Under the right conditions in shallow water, you might grow needles upward from a small opening, a rare phenomenon that shows how flow and geometry guide growth when cold air cools the top faster than the bulk. If you try to save your supercooled sample by moving it to the table when it isn't ready, you'll learn how sensitive the state is. A bump, a swirl, or a flake drifting in is enough to end the poise. And once the front starts, there is no easy pause button. Change cascades. Yet the fragility is precisely why the effect is useful. Scientists and food engineers use controlled supercooling to keep products unfrozen, but safely cold, delaying ice formation until transport or presentation. Doctors use related ideas in cryopreservation, where the goal is to avoid ice crystals that can damage cells by keeping water in a glassy, ordered but not crystalline state. Weather teams seed clouds with microscopic particles to encourage supercooled droplets to freeze and fall as snow rather than glaze roads as ice. None of these require you to believe anything mystical. They invite you to notice that cold and frozen are cousins, not twins, and that the bridge between them is built or broken by structure. Safety matters here too. Never chill sealed glass bottles. They can shatter when ice expands. Use flexible plastic and handle it gently. Never put your face over a bottle as you open it. Avoid very deep freezes or long times that drive everything into rock. And do not supercool carbonated beverages in a closed container because they can gush or burst. A thin glove helps if you're allergic to cold. The feeling you leave with after a clean run is more than a party trick. It's a template for how change appears in other corners of life. Conditions can be ripe for transformation, yet nothing happens until a clear seed arrives. Once the seed exists, growth can be shockingly fast, and the release carries its own warmth that reshapes conditions for what follows. If you pour the last of your supercooled water over a line of ice cubes and watch the clear stream harden into a white ribbon that grows upstream, consider the quiet message there. Many moments are waiting for pattern, not pressure, and sometimes the most powerful act is not pushing harder, but placing the right starting point in the right place and letting nature take it from there. Cymatics, sound painting geometry. Scatter a pinch of salt across a thin metal plate. Touch a small speaker or tone driver to its edge, and slowly sweep the pitch from low to high until the surface begins to hum. And then the quiet miracle appears. The grains jump, skate, and finally settle into crisp white lines and empty dark corridors. A map drawn by sound alone, as if an invisible pencil were tracing the plate's preferred shapes. This is cymatics, the art and science of making vibration visible. And once you see it honestly, without myths, without grand claims, you realize it is not about magic symbols, but about how matter arranges itself when pushed in rhythm. The rule is simple but deep. When you feed energy to a surface at certain favorite pitches, the material organizes into standing patterns where some places barely move and others swing wide. The salt or sand migrates to the calm zones because each grain is bounced out of the busy regions and gradually herded toward the lines of least motion. So what your eyes read as a drawing is really a census of stillness. Change the pitch a little and the pattern snaps to a new design. Change the plate and the entire gallery changes again. A square sheet sings differently than a circle. A pizza pan with a rolled lip favors one family of images, while a flat steel sheet favors another. And a plate clamped at the corners reveals designs that disappear if you hold it at the center. The boundaries tell the story. Fix an edge and you force it to stay quiet there. Leave it free and it can participate, adding curves and petals that would be impossible in a stricter frame. Even where you place the driver matters. If you push at a spot that is naturally calm for a given pattern, that pattern resists you. Slide the driver to a livelier area and it leaps to life. This is why instrument makers have used vibration maps for centuries. Long before anyone had a video app to slow things down, Ernst Chladni bowed the edge of metal plates and sprinkled sand to reveal the same shapes you are watching now. Using the patterns to tune and test, and modern luthiers tap and read wood plates in a similar spirit, not because the lines are mystical, but because they reveal stiffness, mass, and how a part will contribute to a voice. You can build a careful version at home without wrecking your hearing. A small speaker or a purpose-built exciter taped to the underside or edge of a light plate, a tone generator app to sweep slowly, a shallow sprinkle of fine salt or flour, and soft ear protection because even modest sound near your hands grows tiring. Start low. If nothing orders itself, pause and move your contact point a few centimeters, or rest the plate on thin foam blocks so it can flex freely. When a pattern does appear, it will not fade in like a dimmer. It will click into existence, crisp and sure, the way frost flowers crystallize on glass when conditions finally line up. That click teaches an adult lesson. Systems often have thresholds where behavior flips from mess to clarity, and once you cross one, structure maintains itself with little extra push. Watching salt lines teaches other habits of attention. You notice that increasing pitch usually adds complexity, but not always smoothly. Some steps produce clean symmetric lattices. Others carve spirals or starbursts, and a few give lopsided pictures that settle slowly and then suddenly sharpen, as if the system had to choose a side. You learn that heavier grains resist being herded at gentle motions and require stronger forcing, while powder responds to the faintest whisper and sometimes draws false ghosts from static cling. You learn that a plate with a greasy film behaves differently from a freshly cleaned one, because friction between grain and surface shapes how easily the material can migrate into the quiet lines. You see that the same pattern can be made by stepping down to a lower pitch if you change how the plate is supported, because the true rule is not the number on the dial, but the relationship between the push and the object's own preferences. That word, preferences, is useful here, because it pushes you away from thinking of sound as an abstract wave in the air and towards seeing vibration as a negotiation between energy and structure. The plate does not accept every invitation. It selects, and the selection is written in geometry, length and width, thickness and material, how edges are held, where mass is added, where stiffness varies. Engineers use that selectiveness every day. They excite airplane panels and car hoods with shakers to find troublesome modes that might rattle at highway speed. They strengthen a rib here, change a curve there, and the sand map changes with it. In tiny devices, the same logic runs sensors that measure acceleration or rotation, each little silicon plate built to prefer a certain motion that a circuit can read. In architecture and acoustics, knowing a room's favored vibrations helps tame boomy notes and dead zones. In non-destructive testing, ultrasonic patterns expose flaws because a crack changes the local preferences and the map gives the defect away without cutting anything open. Liquids carry their own version of cymatics that looks like living lace. Sprinkle light powder on a shallow dish of water, rest it on a small transducer, and sweep. At modest settings, the surface draws circles, grids, and flower petals, the topography of tiny waves that face and reinforce one another. Push a bit harder, and a famous instability wakes up. The surface begins to dance at half the driving rate, flipping up and down on alternating beats, and the powder tells you where the crests repeat. This is not a claim that sound heals, or that a single tone unlocks a secret alphabet. It is a clear, repeatable demonstration that forcing a system rhythmically can coax it into stable, low-energy patterns that are both beautiful and informative. Beauty helps you learn because it keeps you still long enough to notice the rules. Safety keeps you honest. Protect your ears, keep volumes low, and avoid clamping anything to delicate electronics that were not designed for this. Never drive a speaker cone so hard that it rattles or smells hot. Do not dump abrasive grit into a cherished woofer. Use separate plates and simple exciters you can sacrifice. If you crave color without claims, replace salt with fine sugar and shine a raking light so the lines sparkle, or lightly mist the plate and let the water beads be your grains. Every substitution teaches you something about friction, momentum, and how different media respond. It is tempting to search for a single frequency that makes a perfect mandala, but the truth is richer. Every object owns a family of voices, and the picture you get is the one your setup invites today. When you finish and sweep the salt into a jar, take a last look at the clean plate. Plain metal, no lines, no flowers, no stars. The images are gone because you are no longer asking the question that produced them. That may be the quietest gift Cymatics gives you. Geometry is not carved into the world waiting to be found like a fossil. It appears when you push and hold conditions just right, and then it withdraws when you stop. In that rhythm, you learn something practical and human. Order is not only discovered, but made, and with patient, gentle energy, you can help it appear. Not by forcing a shape you already want, but by learning the preferences of the thing in front of you and meeting them at the right pitch. Oobleck, a liquid you can punch. You don't expect a bowl of kitchen slurry to choose when to be soft and when to be stubborn, but the moment you drive your fingers in fast and feel the surface resist like wood, then relax and watch your hands sink as if into cream, you meet Oobleck, a homemade fluid that teaches you in one touch that liquid isn't a promise, it's a negotiation. Mix plain cornstarch with water until it flows like heavy cream. Stir gently until the lumps vanish, and you've built a non-Newtonian material whose thickness depends on how you treat it. Slow motions let it ooze. Sudden motions make it lock. What's happening inside is more than a party trick. Cornstarch is packed with tiny, hard particles suspended in water. When you move slowly, the water has time to slip between grains and act as a lubricant. So the mix behaves like a thick soup, and you can rake channels with your fingertips. When you punch, squeeze, or shear it quickly, the water can't evacuate the gaps fast enough. Particles crowd together and jam, and the mixture pushes back like a solid. Rheologists call this shear thickening, and in Oobleck it can be dramatic, nearly discontinuous. So a sharp tap turns the bowl into a drumhead, while the same tap slowed to a press leaves a deep, glossy dent that lazily heals. Try a few tests to feel the rules without a single equation. Scoop some into your palm and squeeze hard. A pale, crumbly solid forms between your fingers, then melts to a drip when you stop squeezing. Lay a sheet of plastic over a speaker, add a shallow puddle, and play a bass tone at gentle volume. Soft peaks stand up and shimmy. Raise the volume slowly and the peaks stiffen, lowering when the sound relents. Pinch a bit between thumb and forefinger and roll a quick little marble. Hold still and it slumps into a puddle, a miniature time lapse of firmness giving way to flow. Spread a thin layer on a plate, then strike the edge with a spoon. A clean starburst cracks outward like in brittle glass, yet a second later the lines soften as the surface forgets the shock. If you've seen videos of people sprinting across a pool of Oobleck, you're watching the same physics at a grand scale. Each footfall delivers a sudden, high-stress pulse that jams the grains into a supporting scaffold for the instant the foot needs it. Pause mid-pool and you'll sink, because you've traded impact for patience, and patience invites the mixture to behave like a liquid again. Although the recipe is playful, the behavior maps onto serious uses. Engineers explore shear thickening fluids for flexible protective gear, impregnate fabric with a suspension of hard nanoparticles, and under normal motion, it flexes like cloth, but under a blow it stiffens and spreads the force, helpful for padded sportswear or certain kinds of armor and cut-resistant gloves. In robotics, dampers filled with such suspensions can absorb sudden jolts without making normal movements sluggish. In manufacturing, these fluids can tame chatter in polishing or drilling by biting down only when vibration spikes. Oobleck won't replace those. Its cornstarch grains are too big and it dries out. But it's a generous teacher for the idea that materials can volunteer strength on demand and then let go. To keep your kitchen safe and your curiosity intact, set a few gentle boundaries. Mix in a wide bowl placed on a tray to catch splashes. Wear an apron. Keep the floor dry to avoid slips. And when you're done, don't pour sludge down the drain. Dilute a cup at a time with plenty of water and dispose in the trash, or let it dry to a cake and break it into the bin. Starch in pipes is a plumber's retirement plan. If the bowl thickens while you play, add a spoonful of water and stir. If it runs thin, dust in more starch. Temperature matters less than timing, but you'll notice a cooler mix is a tad thicker because water moves more sluggishly between grains. You can also explore boundaries that stretch your intuition without repeating earlier lessons. Draw your finger slowly across the surface and note the quiet valley that trails you. Now sweep fast and watch a ridge rise in front of your finger like a snowplow. The material jams ahead of the motion, redirecting force sideways and up. Toss in a few clean glass marbles and try to stir in a circle. At low speed, they raft along smoothly. At high speed, the whole batch shudders and the spoon stalls as if you've hit gravel. Lift the spoon quickly and a cone rises with it, then collapses in folds that remember your path for a breath before smoothing out. For a visual that sticks, dust the top lightly with cocoa powder and strike the side of the bowl with a flat palm. A crisp ring clears as the jammed front shoves outward. Then the powder drifts back as the surface relaxes, a slow-motion signature of shock and recovery. And here's a twist you might not expect. If you switch media, say, a mixture of water with very smooth, round particles instead of irregular starch, the thickening can be weaker because smooth spheres slide more easily. Oobleck's satisfying snap owes much to the size, shape, and slight roughness of cornstarch grains, which build strong force chains under stress. It's tempting to lump all non-Newtonian behavior together, but Oobleck is only one quadrant of a bigger map. Some fluids thin when you stir them. Paint and ketchup flow more readily under motion, which is why a shake or tap helps them spread. Others take time to thicken if kept under stress, and some recover slowly after motion stops, leaving trails that persist before smoothing. Clays and geols often do this. Learn Oobleck first and you'll feel the axes, how hard you push, how fast you push, and how long you keep pushing. The reflections you carry away are practical, not mystical. You learn that resistance is not just about mass or hardness. It can be about timing. Short, sharp efforts get a different answer than steady pressure. You learn that systems can build temporary skeletons when stressed and let them dissolve when the moment passes, which is why a sharp rap quiets a wobbly mixing bowl more than a gentle, steady hand, and why stomping on wet sand briefly firms it under your heel, while standing still lets water creep up and soften your footing. You learn that flow can hide structure that appears only when needed, and that the same material can support or surrender depending on how you ask. And if you're using this for focus or sleep, there's a softer consolation in the bowl. You can hold both things at once, firmness and yield, and choose with your tempo which one you get. When you finish, level the surface with a slow sweep and watch it gloss over, silent again. In your hands, you held a small, honest paradox that required no symbols to explain itself, only a willingness to test. Push hard, it pushes back. Wait, and it lets go. That simple lesson has a way of leaving the kitchen with you. Sometimes the path through isn't brute force, but a change of pace. And sometimes the smartest thing a liquid can do is become solid, just long enough to keep you from sinking. Cartesian diver. Squeeze to sink on command. Seal a clear plastic bottle full of water. Drop in a tiny diver that floats with just its nose peeking above the surface, and then wrap your hand around the bottle and squeeze. The diver obeys like a trained creature, slipping downward on command and hovering wherever you stop. Relax your grip and it rises as if remembering how to breathe. And in that simple, obedient motion, you can feel the fundamentals of buoyancy and pressure locked together in your fingertips. No formulas required, just honest cause and effect you can test as many times as you like. The diver is usually a glass eyedropper, a pen cap sealed with a bit of clay, or a ketchup packet, anything that traps a small bubble so its overall density sits just a hair below water's, because that hair is the difference between floating and sinking. When you squeeze the bottle, you raise the pressure in the water. The pressure squeezes the air bubble inside the diver. The bubble shrinks. The diver's average density tips from just lighter than water to just heavier, and down it goes. Let go, and the bubble relaxes. The volume recovers. Density falls below the threshold again, and the diver glides back up. What makes this more than a toy is how sensitive it is. A barely there squeeze can hold the diver mid-water. A stronger squeeze lands it on the bottom, and a practiced hand can park it at any depth, turning your palm into a throttle for buoyancy. Tilt the bottle and you'll notice you can steer along the bottom and scrape past pebbles, which teaches a second lesson, that water transmits pressure evenly, so your grip on the sidewall becomes a uniform nudge felt everywhere inside. If your first build refuses to sink, tune it like a mechanic. Add or remove a grain of clay, trap a slightly bigger bubble, or crack the cap open to bleed a film of water from the bottle so the diver starts a bit lower. The sweet spot is float by a whisper, because then a small squeeze is enough to cross the line. Once it works, you can turn the desk into a lab, swap the water for salt water, and watch the same squeeze do less, because salt water is denser. Your diver now needs a stronger compression to match that density threshold. A kitchen-scale version of why floating is easier in the ocean than in a lake. Warm the bottle under a lamp and try again. The diver becomes more buoyant because the trapped air expands with heat, so a firmer grip is needed to sink it. Now you've discovered that temperature too can be a knob on buoyancy. Use two divers tuned differently and race them with gentle pulses. The one with the smaller bubble responds faster to pressure changes, but demands a stronger squeeze to start moving, while the big bubble diver is touchy and overshoots, just like two hot air balloons with different ballast. Dot the bottle with a marker to mark depth stations, and learn to hold at each line with the right pressure. a fine motor practice that sneaks physics into your hands. If you think the squeeze only compresses air, add a drop of food coloring near the diver and watch closely. The color barely stirs when you squeeze because the water itself is very hard to compress. Almost all the action happens in that compliant bubble, a tiny spring hidden in the diver. Replace the dropper with a solid bead and you'll feel almost nothing move under your grip. A comparison that makes the true hero unmistakable. For a visual that imprints, wrap the diver's upper bubble with a loop of bright tape or draw a tiny scale on the dropper. Then film it side on. Each squeeze trims the bubble, and you can pause the video and measure how little shrinkage it takes to flip the buoyancy. Millimeters, not centimeters. Proof that thresholds often hinge on small changes in the right place. The same principle shows up wherever people or animals need to rise and sink with control. A fish's swim bladder is a living diver. It adds or removes gas to adjust average density and hold a depth without constant effort. A submarine floods ballast tanks to dive and forces water out with compressed air to surface. A scuba diver learns to feather a buoyancy control jacket, adding a breath to hover a meter above coral and venting a breath to settle gently on sand, discovering the same hairline balance you feel in your hand. You can even model failures safely. Make a diver with a slow leak, squeeze to sink it, and watch it refuse to rise fully because water crept in and quietly raised its weight. Now you have a miniature lesson in maintenance and why real ballast systems need checks for trapped water or stuck valves. The build invites embellishments that teach without preaching. Slip a tiny paper fin on your dropper and you'll see it yaw into any small current as it descends, reminding you that drag and shape matter. Try a bottle with thick walls and one with thin. The thin bottle transmits your squeeze more easily, so the diver is livelier. Put two divers in the same bottle and learn that they don't truly affect each other unless they bump, because the pressure you make is everywhere at once. Add a tiny magnet to the diver's nose and move a steel paperclip outside the bottle to dock at a station. Then feel how a magnet's local pull competes with buoyancy's global rule. If you're tempted to take the trick outdoors, mind simple safety. Use plastic, not glass. Keep the cap snug so a vigorous squeeze doesn't pop the top. Avoid very hot cars or sun-baked rocks that can raise pressure and deform the bottle. And clean the setup thoroughly if you use ketchup packets. Salt and sugar grow a biology experiment you didn't ask for. For a classroom-friendly cleanup, use a pen cap sealed with a pea of modeling clay. Nothing dissolves and you can dry and reuse it for months. The longer you play, the more you'll catch yourself predicting outcomes and then checking them. And that habit, state a guess, press, observe, adjust, is the real treasure here. You'll predict that a squeeze after a long warm-up will demand more force, that a diver will sink faster at first and slower near the bottom because currents calm, that tapping the bottle changes depth, not because you shook the diver, but because tiny pressure pulses echoed inside. Eventually you'll feel something extra, control with almost no effort. The smallest change you can make reliably becomes the most useful, and you discover how finely tuned inputs lead to stable, graceful outcomes, while big, clumsy squeezes overshoot and send the diver bouncing between top and bottom. When you set the bottle down and the water goes still, nothing about your desk announces that you've been working with the same ideas that guide ships, fish, and submersibles. Yet your hands will remember the lesson the next time you watch a scuba diver hover over a reef or a submarine rise in a harbor. Change a pocket of compressible space, shift average density by a whisper, and the whole body answers. Rise and sink become decisions rather than accidents, and the quiet confidence that follows is not a trick. It's understanding you can feel. Pepper and soap. Surface tension makes water run away. Dust a calm bowl of water with a snowfall of ground pepper. Touch a soap-wet fingertip to the center, and watch the entire surface flinch. The pepper flees to the edges as if your finger scared the liquid itself. A tiny shock that feels like a magic trick until you learn the rule you just triggered. Water hates uneven tension, and soap creates exactly that. So the surface pulls itself away from the low tension spot and drags anything floating on it along for the ride. What you're seeing is not pepper running and not soap pushing, but a gradient. one side of the surface tugging harder than the other. A little tug of war that the stronger side always wins. Clean water has a high, even surface, tension that behaves like a stretched film, but when a surfactant touches down, its molecules spread, lower the local tension, and break the symmetry, so the rest of the surface yanks back to restore balance, sweeping debris outward in a quick, graceful burst called Marangoni flow. You can feel the logic with common sense before you ever hear the name. A perfectly taut bedsheet lies smooth. Loosen one corner and the fabric near the slack spot wrinkles while the tight areas pull away. Soap does that to a water skin at the scale of molecules. Pepper just makes the motion visible because its tiny grains are hydrophobic, refusing to get wet. So they sit right on the surface like little rafts and trace the current lines your eyes would otherwise miss. The same trick works with dust, cinnamon or poppy seeds. Choose whatever gives you the clearest contrast. Try the basic version first. Fill a wide plate with water. Rain down a thin, even layer of spice, then wait 10 seconds so the surface calms. Touch a clean, dry fingertip to the center, and nothing dramatic happens because the tension is uniform. Now dab your finger in dish soap, shake off the excess, and touch down. Snap. The pepper makes a ring at the rim, and if you lift and touch at a new spot, a second shock front sprints across what's left, weaker but still visible, until the soap film has spread thin and the effect fades. If your first attempt fails, it's telling you something true. Oils on your bowl or invisible surfactants already in the water can flatten the gradient before you begin. Scrub the plate with hot water and a little detergent. Rinse thoroughly and start again with fresh tap water. If your tap is very hard or soft, try filtered water. Keep the soap at the fingertip only. If you pre-mix it into the bowl, there's no difference for the surface to react to. From there, you can turn the table into a small lab without changing the core idea or repeating a past lesson. Warm the water slightly and repeat. The spread is livelier because warmth helps the surfactant molecules migrate faster. Chill the plate in the fridge and the response slows. Sprinkle pepper, then form a tiny soap dot with a toothpick at one edge and watch a one-sided current sweep the field like a wind that arrives from nowhere. Now switch to plain alcohol on the toothpick, and you'll see a similar quick retreat as the drop spreads and evaporates, lowering local surface tension differently, but producing the same pull from the stronger side story. If you want an image that sticks, lay 2 toothpicks on the water surface in a V shape and anchor the tips lightly at the rim. Touch a soap dot between the open ends and the sticks pivot apart as the water slips away from the dot. No hidden motors, just the surface rearranging to get rid of the gradient you created. For a slow-motion mural, use whole milk in a shallow dish, dot the center with drops of food coloring, and introduce a pinpoint of soap. Colors explode outward, then curve and branch as fresh swirls of low tension keep forming, and the currents chase the difference. It looks like chemistry painting, and it is, still the same principle, just with fat molecules joining the dance and making the flow complex enough to hold your gaze. Once you trust the effect, you can build a tiny boat to ride it. Cut a paper triangle with a small notch at the rear, float it on clean water, and dip a fine wire loop into soap. Touch a drop right into the notch and the boat shoots forward because the water behind it loses tension and the higher tension water ahead pulls harder. Another lesson in how asymmetry, not force, does the work. Try again after the surface is contaminated with soap and the boat crawls or stalls. Proof that you can't cheat a gradient that no longer exists. All the while, keep a light hand with safety and cleanup. Use drops, not puddles. Keep soap out of eyes. Wipe dishes well so the next experiment starts from a clean slate. And resist the temptation to pour half the bottle just to make the pepper move more. The effect needs a difference, not an overdose. If you're curious about why pepper spreads into tidy wedges and lanes rather than a smooth ring, study the edges. The bowl's rim pins the flow, Small eddies form as the water races and slows, and the grains self-organize into corridors where drag is lowest. In a square dish, you may see 4 preferred arms racing toward the corners, simply because geometry sets where water can most easily leave the center. Add a tiny drop of oil to the middle before the soap and watch the plot twist. The pepper may cluster around the oil, then leap away when soap arrives, because oil spreads too and changes the local tension before the surfactant gets its turn. What you're watching is competition between agents, each writing its own pattern of ease and strain into the same stretched skin. This small experiment carries real-world echoes that matter more than the parlor trick. Tears of wine creeping up a glass and falling in beads happen because alcohol evaporates at the rim, raising surface tension locally and pulling liquid upward until the drops grow heavy and fall. Silk moth larvae and tiny water-walking insects use natural surfactants to lay scent trails that steer or stop neighbors. Engineers design coatings that resist or invite spreading to keep airplane wings clear of ice, medical devices free of unwanted films, and camera lenses from fogging. Even your own breath can steer droplets on a surface because humidity changes how easily water stretches and flows, and the gradient returns. Most of all, this teaches an adult habit of attention. Effects you can't see directly. Tiny molecules arranging themselves. Leave signatures you can make plain with tracers and a gentle setup. And when you want motion without pushing, creating a difference is often smarter than applying a shove. End your session by rinsing the plate and trying one last touch with a clean finger. Silence again, which is its own lesson. Once the surface is evenly relaxed, there's nothing left to chase, and the water lies still because you've removed the imbalance that gave it purpose. The memory to keep isn't that pepper flees soap. It's that systems respond to gradients, and you can make or erase those gradients with very small inputs. That's a portable idea. When you want change, don't hammer the whole field. Alter one property in one place and let the difference do the pulling. In a quiet kitchen with a bowl, a pinch of spice, and a drop of detergent, you just watched a clear liquid demonstrate how the world often really moves. Not by force alone, but by the patient power of unevenness seeking balance. Floating paperclip. Liquid skin strong enough for steel. Balance a small steel paperclip on the glossy top of a bowl of water, and it feels like you've cheated the universe. Metal denser than water should sink, yet there it rests, glinting on a skin so taut it dimples under the load without breaking. A quiet proof that liquids carry their own kind of strength, and that strength lives at the surface. You can do this with no tricks beyond patience. Degrease a clip with hot water and a touch of detergent. Rinse it thoroughly so no soap remains. Dry it. Then bend a tiny L-shaped handle from a strip of paper or the corner of a sticky note. Set the clip on the paper raft and lower the raft until the clip kisses the water. Slide the paper away and, if your hands are calm and the surface clean, the clip will stay, riding a shallow crater that you can read in the reflections, like a moon resting on soft asphalt. What's holding it is not buoyancy in the usual sense. The metal displaces almost no volume because it barely sinks. So the familiar up thrust equals the weight of displaced water story can't be the hero here. Instead, a different helper steps forward. Water's surface tension. The energy cost of stretching that microscopic skin where air and liquid meet. Surface molecules have fewer neighbors to cling to than those deep inside, so they huddle more tightly. And the result is a film that behaves like an elastic sheet. Touch it and it resists being widened. Pull it inward and it resists being wrinkled. And along the rim that wraps the paperclip, that resistance converts into an upward pull around the entire perimeter, like a crowd of tiny hands gripping the wire from all sides. You can see that pull in the shape of the meniscus. Light glances off a ring of bright highlights, where the surface bends up against the metal, steeper near sharp corners, and gentler on long straight sections. If you dust the water lightly with talc or flour before you set the clip, the grains gather into a faint halo around the meniscus, mapping the slope your eyes can't quite resolve. The trick to a reliable float is to work with this perimeter, not against it. Thin, smooth, clean wires float best because they maximize edge length for their weight. That's why a sewing needle or a razor blade is even easier than a chunky binder clip. More rim to pull on, less mass per millimeter to hold. Cleanliness matters because grease lowers surface tension and weakens your invisible rope. Warmth matters because hot water relaxes the film slightly, tilting the balance towards sinking. Vibration matters because a trembling table can shake the meniscus and make the rim slip. If your first attempt fails, reset the conditions rather than forcing the result. Skim the surface with the edge of a clean sheet to lift off dust. Wipe the clip again, cool the water a little, and try the paper raft method instead of fingers. Fingers pierce the film and leave trails that take a moment to heal. Once the clip is riding, study how the system negotiates its piece. The wire pushes down and the surface gives way, forming a bowl-shaped depression. Along the contact line where metal meets water, the skin pulls upward at a slight angle, and when you add all those tiny upward tugs around the loop, they balance the clip's weight exactly. Nudge the clip gently with a toothpick and you'll feel a sticky hesitation. Contact line. Pinning, because the rim prefers certain positions on a slightly rough wire and resists sliding until you push past a small threshold, after which it jumps and the clip creeps a fraction deeper or shallower. A miniature lesson in how friction and hysteresis live even at calm interfaces. Test the limits thoughtfully. Touch a drop of rubbing alcohol or diluted dish soap to the far side of the bowl, and watch the clip sink almost instantly. By lowering the tension everywhere, you've taken away the upward pull that kept it afloat. Warm the water with your palms until a light haze forms on the bowl, and the clip grows less confident for the same reason. Shake a few grains of salt into the water, and it often helps, not by magic, but by keeping the surface a touch cleaner and changing wetting slightly. Bend two clips into a narrow V, set them far apart, and you'll feel a faint attraction if you connect them with a hair or thin thread. Their menisci slope toward each other, and the liquid hill between them pulls them together, an effect boaters see when floating objects cluster along a shoreline because their weight warps the surface, and the warped surfaces seek company. Try floating two different shapes, and you'll learn that corners are both allies and liabilities. Sharp edges give the rim a ledge to grab, strengthening the pull, but they also focus stress and can be the first places to fail if disturbed. A lightly waxed clip, surprisingly, can float more easily if the wax increases the angle the water meets the metal, letting the surface climb higher up the wire and increase the vertical component of the pull. Wettability is a tuning knob you can feel without ever naming the angle numerically. Flip the story by design and you'll watch the skin lose its grip. Tap the rim with a piece of tissue, and the clip sinks as the paper wicks the surface inward and gives the skin a place to go. Blow across the bowl and ripples nibble at the meniscus until it slips and the wire falls. Wait long enough and dust in the room settles. Tiny surfactants from life in the air relax the film and the clip finally lets go. Not because the metal changed, but because the boundary did. None of this is a party trick divorced from the world beyond the bowl. In microfluidics, engineers fight and harness these same forces to shuttle droplets along channels the width of a hair. In printing and painting, controlling how a liquid meets a surface decides whether a line feathers or stays sharp. In soft robotics and tiny machines, meniscus forces can dominate gravity, turning a drop into a hinge or a pump. In materials research, surfaces are textured, so water either clings like a climber or flees like mercury, building self-cleaning coatings and fog-catching nets that harvest drinking water from dry air. Even the simple confidence that comes from watching the clip ride teaches a habit of mind. Strength isn't always a bulk property. Sometimes it's concentrated at the thin edge where two worlds meet, and small changes, temperature by a few degrees, a trace of soap, a cleaner rim, decide outcomes more surely than heavy hands. If you want to leave with a map for future experiments, hold 3 images in your head. First, the clean float, a cool bowl, a degreased wire, a paper raft, a depression that glows with reflected light, and a rim that does real work. Second, the near miss, a clip that wobbles as the contact line slides and catches, teaching you where subtle roughness lives and how patience steadies fragile systems. Third, the deliberate sink, a single drop that softens the film and removes the scaffold, showing you how a uniform change across the whole surface can undo what a uniform pull once held up. When you lift the clip and dry it on a towel, the water goes back to looking like ordinary water, but your intuition is different. You've felt the difference between volume and boundary, between pushing from within and pulling along an edge, and you've learned that a liquid can be strong in exactly the way you need it to be if you ask carefully. That's the lesson a floating paperclip carries better than any equation. Pay attention to the skin of things, because that's often where the leverage hides. Index matching glass. Make objects vanish in oil. Slip a glass rod into a clear beaker of ordinary water, and you'll still see it bend the scene like a wand. But lower the same rod into a beaker of the right oil and click. It seems to dissolve into the liquid, edges softening, body fading, until only a faint seam and a few clinging bubbles give it away. Nothing supernatural happened. You simply removed the reason your eyes normally notice glass at all, a difference in how the two materials bend and reflect light. When light crosses from one medium to another, two things decide how visible that boundary is. How much the light changes direction, and how much bounces off instead of going through. And both are controlled by a material property called refractive index, a simple number that says how much slower light travels in that substance than in vacuum. Air's index is just above 1, water's around 1.33, many glasses around 1.5, and common oils spread from about 1.45 to 1.52 depending on chemistry. When a beam goes from air to glass or from water to glass, it bends and some of it reflects, so the boundary announces itself with distorted backgrounds and glints. If you instead choose a liquid whose index nearly matches the glass, the beam barely bends and hardly reflects at that interface. So the glass stops acting like a lens and starts acting like more liquid. Your brain, which is brilliant at detecting boundaries by tracking changes in brightness and direction, now finds almost nothing to latch onto and interprets the place where glass ends and oil begins as empty. You can test this at home without equations or special lamps, only care and patience. Find a short piece of clear borosilicate glass, fill one beaker with vegetable oil and another with a thicker, higher index liquid like glycerin or sugar syrup, and a third with baby oil or clear mineral oil. Dip the rod slowly into each and compare. In vegetable oil, the rod will soften but remain obvious because the index gap is still large. In glycerin or a dense sugar syrup, it fades further. In some brands of baby oil or mineral oil, it nearly vanishes because their indexes come closer to that of many glasses. Temperature nudges the effect. Warmer liquids usually have slightly lower index, cooler slightly higher, so chilling the beaker in the fridge can improve a near miss. Cleanliness matters more than you expect. Any film of grease, dust, or micro scratches on the glass scatters light and reveals the outline. Wash the rod with dish soap, rinse, and handle it by the ends. When you first immerse, tiny bubbles can cling to floors and draw a dotted line. Gently tap the beaker or brush bubbles away with a soft brush, and you'll see the last hints disappear. You learn quickly that invisible isn't all or nothing. The body may vanish while the ends stay visible because the cut faces still reflect a little light straight back at you. And if the rod is molded with a slightly different glass composition than your oil's ideal match, a thin halo persists that changes with viewing angle. That residual glow is a teacher, not a failure. It reminds you that real materials come in families, not perfect pairs, and that index matching is about narrow differences, not magic. Once you've felt the basic trick, you start spotting the same principle across the world. Microscopes use immersion oil, whose index is tuned to match the glass of the slide and the objective lens. With the gap erased, light from your specimen slips through with less bending and less waste, boosting sharpness and brightness at high magnification. Fiber optic technicians smear index-matching gel between connectors, so a clean beam crosses the tiny air gap without a flash of back reflection that would otherwise confuse detectors. Underwater photographers press flat ports against water instead of domes to control how refraction magnifies and shifts a scene. Conservators fill chips in crystal with adhesives matched to the host glass, so repairs fade from sight. Even your phone screen's laminated. Layers rely on optically clear adhesives whose indexes are chosen to reduce the ghostly second image sum. Older displays had when air gaps reflected a portion of the light back at you. Nature plays the same game with different stakes. Many transparent sea creatures are not perfectly invisible. They are index similar. Their tissues are close enough to seawater that they throw only faint clues at predators. A soft shimmer at an edge rather than a hard silhouette, especially effective in the diffuse light of open water. Snow turns white because ice crystals don't index match the air they trap. Every ice-air boundary scatters light, so a handful of clear crystals becomes a bright puff. Drop snow into water, and it loses some brilliance as the mismatch shrinks. If you've ever dripped oil between two cracked pieces of a glass screen and watched the crack fade, you've used index matching as a bandage. Specialized resins do the same permanently, wicking into fractures and closing them optically even when the structure is still weaker than new. The failures teach as clearly as the successes. A faceted marble dropped into a matching oil can still wink at you because the sharp angles throw light toward your eyes even if the bulk boundaries are quiet. A scratched beaker remains obvious because roughness creates lots of micro interfaces with slightly different angles that toss light around like glitter. A cloudy, seeded glass never fully disappears because tiny crystals within have a different index from the host, and those grains scatter light the oil can't tame. You can even flip the trick deliberately. To make hidden chips pop for inspection, dunk glass in a liquid with a very different index, and shine a narrow flashlight. Suddenly every flaw blazes because the mismatch is exaggerated. As you play, keep the table safe and the experiment honest. Avoid heating oils on a stove. Keep flammable liquids away from sparks. Use a tray to catch spills, gloves to keep hands clean, and store bottles with labels so you don't confuse cooking oil with solvent. Never immerse borosilicate in strong solvents that can craze it. And when you're done, strain any shards, cap the beakers, and wipe lenses or phone cameras you used to film. Oil mists travel farther than you think. If you want to turn the lesson into a portable habit of mind, notice how often clarity comes from removing a contrast rather than adding force. When there's no difference to bend or reflect a path, light passes without announcing the border. You can match more than glass. Match expectations to conditions and friction falls. Match presentation to context and distractions drop away. Match interfaces, literal or social, and signals cross cleanly. But keep your science hat on. Some edges should stay visible. In engineering, you eliminate reflections where you want unbroken transmission, and you add structured mismatches, anti-reflection textures, diffusers, frosts, where you need information, grip or privacy. Standing over your beaker with the vanishing rod, you feel this balance in your eyes. Remove just enough contrast, and the object becomes part of its environment. Remove too much, and you also remove the cues you need to grasp or guard it. When you lift the rod back into the air and it snaps into visibility, the trick feels undone, yet your intuition is newly tuned. You don't think magic oil, you think border conditions, and you know that what you see depends as much on the space between things as on the things themselves. That's a quiet, sturdy kind of knowledge, the sort you can carry into any room where something isn't being seen and ask, gently, whether the index is simply mismatched. DVD diffraction. Build a rainbow spectrum at home. Hold an old DVD up to a window and tilt it until the room spills into color, and you'll realize you've been keeping a laboratory in your junk drawer, a rainbow machine stamped into plastic, because those tight, shimmering lines on a disc act like a precision mirror that teases white light apart into its hidden ingredients. And with a few kitchen scraps, you can build a spectroscope that maps the secret recipe of lamps, screens, and even sunlight onto your wall. Start with the why before the how. The DVD isn't smooth. It's a spiral of microscopic ridges packed so closely together that they behave like a ruled mirror, bouncing different colors at slightly different angles. Red, being the longer wave, leaves at one slant, blue at another, and your eye, exquisitely sensitive to direction, separates them into a fan of hues. No batteries, no formulas, just structure doing the sorting. Now make it practical. Grab a cereal box, 2 pieces of stiff foil, tape, scissors, and a scratched disc you won't miss. On the top of the box, cut a narrow slot and tape the 2 foil pieces inside to form an adjustable slit, thin as a hair if you can manage, because a tidy, skinny beam gives you clean, sharp color. Crack the DVD gently, score it with scissors and bend, or stick packing tape to the label side and peel until a clear wedge separates from the backing. You're after a translucent slice that shows faint lines when you tilt it under a lamp. Tape that wedge inside the box at a slant near an eye hole you cut on the side. Aim the slit toward a bright, diffuse source, and put your eye to the hole. Across the dark interior, a painted ribbon spreads itself, red melting into orange, then green, then blue and violet, like a tiny dawn you can hold still with your hand. This is your first instrument. Turn it toward different lights, and the ribbon changes character in ways that teach more than a textbook paragraph. An old incandescent glow or a heated filament flashlight produces a smooth, unbroken sweep, because hot filaments throw a continuous mix of colors. A white LED usually shows a strong blue peak with a broad smear of green and yellow born from phosphors, revealing that white was engineered, not pure. Compact fluorescence and some streetlights surprise you with crisp, bright bars at specific places. Signatures of the gases and coatings inside. Yellow in sodium-rich lamps, greens and reds in phosphor blends. Proof that different technologies make white by different routes. Tilt slightly, and a second, fainter rainbow appears on the other side of the slit image. That's another order, a repeat of the spread at a steeper angle. Your disc can give several if the room is dark and the source bright. If the colors blur together, narrow the slit. If you see only a glare, dim the source or turn the box a few degrees. If nothing appears, be patient with alignment. Small angles matter, and check that your wedge's lines run perpendicular to the slit so they can do their sorting job. From here, the experiments become a tour of real optics without any heavy machinery. Point your scope at the sky on a bright, hazy day. You'll get a soft, nearly continuous ribbon that hints at faint dips where the atmosphere has eaten certain colors. Hard to see without practice, but motivational. Switch to a candle and notice how the orange end dominates because soot glows like a gentle ember. Hold a green highlighter under a small UV torch and watch the spectrum bloom with a fierce green band. Molecules in the ink absorb invisible violet and re-emit visible light, and your box catches the exact color of that gift. Try a phone screen. Drag a white window to full brightness and you'll see comb-like bands because white pixels are clusters of red, green, and blue subpixels. The DVD wedge neatly resolves them into separate peaks, a geometry-based lie detector for screens. Swap discs and you'll feel the engineering in your hand. A CD, with its coarser spiral, gives a rainbow too, but squeezes colors into a tighter fan. A Blu-ray, with finer tracks, spreads them farther, and may reveal more delicate differences, though its layered coating can dim the view, teaching that shrinking the spacing increases separation. Put down the box and try the reflection shortcut. Shine a bright phone flashlight onto an intact DVD and catch the reflected beam on a white wall a meter or two away. As you tilt the disc, a central white spot appears with symmetrical rainbow dots stepping left and right. Real spectra you can play like keys by rocking your wrist. Swap the light for a red laser pointer pointed safely at a far wall and count the bright red spots marching away from the center. More evidence that structure, not the label, is doing the sorting. Now fold safety and craft into your routine. Never stare at the sun or point concentrated sunlight at your face. Avoid lasers toward eyes or reflective surfaces. Cut plastic away from fingers and collect shards. Keep oils off your wedge because fingerprints scatter light and ruin sharpness. Label your box so nobody mistakes it for trash. And if you use a razor to make a crisper slit, sheath it when done. For a cleaner build, replace foil with 2 slivers of thin black card separated by a hair's width, and spray the interior matte black to kill stray reflections. For a classroom show, put the slit near one end and the eye hole near the other so students can share the view. As your confidence grows, begin to measure without drowning in math. Tape the box to a table facing a fixed lamp. Mark where red, green, and blue land on the inside wall, and note the distances with a ruler. Repeat with a different lamp and compare the spread and the relative brightness of bands. Qualitative becomes comparative, and comparative becomes quantitative the moment you care enough to keep notes. you'll discover that everyday white sources are wildly different under the hood. That color is not a single thing but a weighted blend, and that your eyes have been graciously hiding those differences, so pages and rooms look normal. The disc simply removes the kindness and shows the ingredients. The deeper lesson hides in the simplicity. A rainbow doesn't require prisms cut like diamonds or fancy formulas, just a regular pattern and patience. The pattern in a DVD was designed to store movies, but physics doesn't care. It will happily turn any fine, repetitive structure into a color sorter. That's an empowering way to move through the world. When you want to reveal what's really in a mixed signal, light, sound, even ideas, split it by a structure that treats components differently and look at the spread. When you set the scope down and the box becomes a box again, your eye won't quite go back to trusting white as one thing. And that's a good change. You've built a pocket instrument that makes the invisible honest, and the next time a streetlight hums orange over wet pavement, or a daylight bulb feels too clinical, you'll know why, and you'll know you can prove it with a cereal box and a broken disc. Water glass prism, cast a room-size rainbow. Tip, a plain drinking glass with water, so the rim catches a shaft of daylight and you can turn a blank wall into a slow-breathing painting. Bands of red through violet stretch across the room, sliding as you tilt your wrist. A homemade prism big enough to walk through, and the first surprise is how little you need. Clear water, a clean container, a narrow beam, and patience. The second is how much you learn when the colors leave the page and climb your furniture. Start with a scene you can control. Darken the room slightly. Tape a piece of white paper to a wall as your screen, and shape a window's light with a simple slit cut in cardboard, thin and tall, like the gap between curtains, so the beam that enters your glass is tidy. Fill the glass to the brim and hold it so the incoming strip of white light skims the rim and dives into the water at an angle, then tilt and sidestep until the far wall wakes up with color. Why does it work? Because water bends different colors by slightly different amounts. Blue and violet bend a bit more than red, so the tight white band that enters your makeshift prism fans out inside and exits as a spread. The glass itself doesn't make color. It separates the mix that was already there, and you can feel that truth with your hands as the spectrum sharpens when the slit is skinny and softens when the slit is wide. Swap the glass for a rectangular vase or an aquarium and the control gets sweeter. Straight sides behave more like the flat faces of a true prism, so small tilts give smooth changes instead of sudden jumps. Use a flashlight with a piece of paper taped over the lens and a pinhole punched through the center to stand in for the window if the day is dull, and you'll still paint a gentle rainbow. Though it will be dimmer, light that spreads out must share its brightness. There are small tricks that turn curiosity into understanding without a single symbol. Slip a square of clear plastic under one side of the glass to tilt it a degree or two, and watch the red edge climb the wall while the blue edge lingers. Now tilt the other way, and the low end of the spectrum stretches while the high end compresses, teaching you that geometry decides who gets room to breathe. Set a small mirror in the bottom of a bowl of water. Aim your slit beam onto the mirror through the water and bounce the light to the ceiling. The mirror returns the beam already colored by its trip in and out, and the overhead spread is often wider and cleaner because the path is longer. Walk under it and you're inside the explanation. Add a few drops of milk to the water and the beam itself becomes visible inside the glass as a pale ribbon, a safe way to see the path. Wait too long and the milk scatters everything into haze, so keep the amount tiny and refresh the water when the ribbon turns cloudy. A short lesson in how particles ruin clarity by sending light everywhere. If the spectrum looks faint, it's telling you something accurate. Room-size rainbows are generous in area and therefore gentle in brightness. Move the glass closer to the wall to tighten the image and it brightens. Darken the room a touch more and it snaps into contrast. Patience and small adjustments do more than brute force here. There is drama hiding in the edges too. Roll the glass until the beam inside strikes the inner surface at a glancing angle, and for a moment that boundary behaves like a perfect mirror. Total internal reflection. Flipping the path and stretching the colors in a new direction. Small bubbles on the surface spoil the trick because they break the smooth interface. so skim them off with a strip of paper and watch the effect recover. If you want to connect the room's show to the skies, take a hose outside when the sun is low, mist a fine spray, and slowly turn your back to the sun until a bow rises in front of you. The same rule from your glass plays out in a cloud of round droplets, but with an extra flourish. The light enters each tiny sphere, reflects once inside, and exits as a set of directions where certain colors concentrate. So you see a bright arc with red on the outer rim and blue on the inner. Change droplet size and the bow's sharpness shifts because scattering adds grain to the edges. Take a step and the bow follows because it depends on your geometry. Each person's rainbow is anchored to their own eye. Back indoors, try different liquids and watch trade-offs replace myths. Sugar water thickened to syrup bends more strongly than tap water, so your spectrum spreads farther at the same tilt. But the extra thickness often adds subtle ripples that blur the edges. Isopropyl alcohol bends less than water, so the colors crowd together and dim. Mineral oil lives in between but can yellow the view. Every choice is a negotiation between separation and clarity, and you'll trust that with your eyes after 5 minutes of swapping beakers. Craft matters in a way that teaches engineering by feel. Clean glass with a drop of dish soap and rinse, well to banish films that scatter light into a gauze. Wipe the slit's edges so the beam is crisp. Line the inside of your cardboard window with black tape to tame stray reflections. Never aim concentrated sunlight into anyone's face or onto flammables. Indirect or shaded light is ample. Hold the glass by its base to keep fingerprints off the light path. And keep a towel nearby, because water will go where it pleases when you hit the sweet angle. Once you're comfortable, start reading with your instrument. Aim the setup at a warm desk lamp, and the red-orange end fattens. At a white LED panel, and a blue-green plateau grows wide. At the overcast sky, and the ribbon smooths from end to end. Move your screen closer and farther to see how the colors stretch or squeeze. Then pencil tiny marks on the paper where particular hues land for one source and compare them with another. Suddenly your living room holds a repeatable measurement, not just a pretty picture. You can even borrow a page from photographers. Place a clear glass of water on a sunny windowsill and watch bright teardrops of light dance on the table. The sharp, curved highlights are caustics, places where refraction focuses light into bright filaments. Shift the glass and the pattern writhes like a living thing. The colors that fringe these caustics, faint but real, are dispersion speaking in cursive instead of block letters. A cousin to your wall-size bow. And there's a philosophical echo soft enough for bedtime. The rainbow you cast is not inside the glass any more than music is inside a violin. It appears because you prepare conditions, beam, angle, clarity, and let the object do what it prefers. Change a detail and the whole composition rewrites itself without drama, which is a pattern you can use outside optics too. When you finally set the glass down and peel the cardboard from the window, the room exhales back into whites and greys. But your seeing has shifted. You won't take white for granted as one thing. You'll read light as a blend whose balance depends on path and boundary. And you'll remember that even a cup of water can unlock structure in something as ordinary as daylight if you ask the question the right way and give the answer space to spread across your wall. Dancing raisins, carbonation toggles, buoyancy. Drop a handful of raisins into a tall glass of fresh seltzer and give yourself a quiet minute. At first they slump at the bottom like pebbles with ambitions. Then, a few bright pearls of gas latch onto the wrinkled skins. The raisins hesitate, shiver, and in a small act of levitation they rise, rotating slowly, until they reach the surface where the bubbles burst with soft applause, and the fruit sinks again to wait for the next lift. It's a looping waltz that looks playful, but it gives you a clean way to feel how tiny changes in what surrounds an object can flip it from too heavy to light enough, and how texture, chemistry, and time decide who gets to move. Your stage is simple: a clear cylinder, a fresh carbonated drink, and raisins that haven't been coated in oil or wax. Your eyes do the rest. The key is the raisin's skin, all those folds and pits that make it such a reliable climber for gas. Fresh seltzer is crowded with dissolved carbon dioxide that wants to escape, and rough spots on the raisin offer easy places to start that escape. tiny shelters where the first bead can form without being swept away. Once started, each bead grows fast, fed by the gas in the liquid. And as dozens of beads collect, they add a lot of volume with very little weight to the raisins package, lowering its average density until the surrounding water and sugar bath considers the whole thing light enough to lift. You can prove that the bubbles, not some secret inside the fruit, do the work. Swirl the glass to shake them off, and a raisin that was mid-rise tumbles down. Wait a breath as new beads gather and the climb resumes. Switch to a smooth glass bead of similar size and it barely participates unless you scratch it, because a polished surface gives gas nowhere to start. Texture is the currency here. Switch from raisins to crinkly pasta, to the rough side of a popcorn kernel, to a small shard of pumice, and you'll collect dance partners that accept bubbles easily. Switch to something slick, and you'll get a stubborn wallflower that needs a nudge like a sprinkle of table salt to seed the first beads. The drink matters too. A freshly opened seltzer or club soda is lively because it holds more gas under pressure, so beads grow quickly and the cycle is brisk. A sweet cola works, but its syrup slows the rise and dampens the popping, because thicker liquids resist bubble growth and movement. A ginger ale that's been open a few minutes still lifts raisins, but the tempo slows as the headspace fills with escaped gas and the pressure difference fades. Temperature is its own dial. Colder liquids hold more dissolved carbon dioxide, so a fridge-chilled bottle gives a patient sustained show with smaller bubbles. A glass at room temperature throws bigger beads that break sooner and may jostle the raisins into spinning somersaults near the surface. If you chill both the glass and the drink, the first cycle will be slower to start but can last longer because the reservoir of gas is generous. If you want to study the thresholds instead of only enjoying the loops, set up 2 columns side by side. Plain seltzer in one, the same seltzer with a single drop of dish soap in the other. In the soapy glass, the bubbles wet the skin differently and pop more easily at the surface, often shortening the rides and changing where beads stick. A household proxy for how surfactants alter bubble behavior in everything from bread dough to wastewater treatment. Or try a glass of tonic water next to a glass of still water with a pinch of baking soda and a squeeze of vinegar to make your own fizz on demand. Watch where beads prefer to form and how long the cycles last. If a raisin refuses to dance, examine it the way a mechanic listens to a stubborn engine. Sometimes a microscopic film of oil on the skin, picked up in packaging or from your fingers, prevents the water from hugging the surface closely, which in turn deprives gas molecules of the nooks where they want to gather. A quick rinse in warm water and a gentle rub with a paper towel can restore the texture you need. Very old soda or a glass with detergent residue can stifle the effect too, teaching you that small, otherwise invisible layers decide macroscopic outcomes. There's a moment worth lingering on when a loaded raisin skims the surface. Bubbles rupture, the raisin tilts, then, instead of drifting away, it drops almost straight down through its own wake, and for a second you can see how the column of fresh, bubble-pour liquid just beneath the surface offers less support than the fizzier depths. So the descent is clean and surprisingly quick. Near the bottom, where the pressure from the overlying liquid is slightly higher, beads will grow a little slower but cling a little harder once they appear, and the raisin's next ascent begins with a gentle roll as if it were checking the balance of weight and lift. You can turn this into a measurement without dulling the charm. Tape a simple scale to the side of the glass and time how long a single raisin spends rising versus resting as the drink goes flat. The ratio slides in favor of resting as the reservoir of gas dwindles, and at the end, the fruit falls dull and stays. Your eyes become instruments, noticing that cycles fade because the fuel is gone, not because the raisin forgot. Extend the idea, and you'll spot cousins in the wild. In sparkling wine, bubbles prefer to appear from specks of lint or tiny scratches in the glass, marching in trains from the same spots again and again. In rivers, mossy stones catch microbubbles that help them lift slightly during noisy flow. In baking, the rough crumb of a batter hosts gas from leavening agents, lightening the whole structure by locking millions of tiny pockets where steam and carbon dioxide can expand. In the opposite direction, a diver's smooth gauge or mask frame resists bubble cling, which is why gear is made with surfaces that won't trap gas and mess with buoyancy. You don't need to name any laws to use the lesson. Systems poised near a tipping point just a bit too heavy to rise, can flip when something changes their effective density, and that something can be as delicate as a collection of tiny attachments. Remove the attachments and the system returns to its old behavior. Keep the setup gentle and safe. No need for glass stemware that can chip, no fizzy drinks aimed at eyes, no surfaces that might stain, and enjoy the way the room quiets when you let one raisin be your metronome. Sink, wait, gather, rise, release, repeat. The longer you watch, the more subtlety you see. How some raisins become leaders because their particular wrinkles make them especially friendly to beads. How the first minute is busiest and later cycles space out. How two raisins can merge into a pair and drift upward like a slow balloon, then split when the beads pop asymmetrically at the surface. And then, when the last bubbles tire and the dance floor empties, you're left with something more than a party trick. A felt sense that motion often emerges not from big pushes, but from small accumulations. That texture is destiny when it comes to where change begins, and that toggling a property as humble as how easily gas can cling is enough to turn the heavy into the buoyant and back. Again, knowledge you can carry into any moment, where the difference between sinking and rising might be as simple as changing what's allowed to stick. Bottle vortex, drain that turns into a tornado. Flip a full plastic bottle upside down and the water hesitates. Glug, pause, glug, until you give it one clean circular twist and the whole mood changes. A clear funnel opens from the cap upward, the glugging stops, and the water pours in a steady, urgent ribbon, while a thin column of air drills down the middle like a tiny tornado. A simple move that turns a clumsy drain into an elegant machine and hands you a lesson in how rotation reorganizes flow, pressure, and even speed. What you've built with that wrist flick is a vortex. The walls of the bottle force the liquid into a spin, and as the water circles the neck, faster near the center and slower at the edges, the whirling motion lowers the pressure along the axis. Centripetal pull must be balanced by a pressure difference, so the free surface caves in, a neat dimple that deepens into a tube. Air rushes up that tube to replace the water leaving below. And because the two can now pass in separate lanes, the awkward stop-start glugging vanishes. You don't need equations to feel the rules, only a few trials with your hands. Start with two identical plastic bottles and a connector to make the classic tornado in a bottle. Fill the top bottle 2/3 with clean water. Screw the pair together, invert, and swirl firmly. If you spin timidly, the funnel will be shallow and wobble. If you overdo it, you'll trap bubbles and cloud the view. The sweet spot is a decisive circular sweep followed by a steady hold. Try additives one at a time to see how properties matter. A spoon of dish detergent creates long-lived bubbles that trace the spiral path down the neck and make the core visible. A pinch of fine glitter or tiny bits of foil outlines the helical lanes without staining anything. A few drops of food coloring left to sit for a minute produce streaks that wrap and stretch as the vortex intensifies, showing how the central column pulls dye into a thread. A tablespoon of glycerin thickens the water, slowing the spin down and giving you a wider, slower funnel that holds its shape. Proof that thicker liquids damp motion and change how quickly a swirl decays against the bottle's walls. Bottle geometry is a quiet teacher too. A wide, smooth-necked bottle forms a broad, stable cone that drains quickly. A narrow, ridged neck makes a skinny, nervous funnel that sometimes breaks and reforms. Fill level changes the show. More water means a taller funnel and greater weight driving the drain, but it also means more time for friction at the walls to steal rotation. So the twist you start with needs to be strong enough to survive the trip to the neck. Watch closely at the cap. Without a vortex, air sneaks in as fat, intermittent bubbles, each one interrupting the outflow and causing the glug. With a vortex, the air column is continuous, so the water exits in a smooth sleeve around it. You've created an organized traffic pattern, up in the middle, down along the sides, and organization is the real trick, not brute force. Now that your hands know the feel, Push deeper with small, honest experiments that won't repeat anything you've tried before. Reverse the spin and see that the funnel forms just as well the other way. The direction doesn't matter at this scale. It's the presence of rotation that counts, not left versus right. So you can safely set aside stories about the planet deciding your sink's swirl. The Earth's twist is too weak to compete with your wrist in a soda bottle. Try starting the spin slowly and then sharply speeding it just as the cone reaches the neck. You'll see the core stretch and narrow because when the central flow speeds up, the pressure along the axis drops further and pulls the air passage tighter. A fingertip sense of how stretching a vortex intensifies it. Add a few small plastic beads and notice how they hover in rings at particular heights. There, the inward pull of the spin and the outward push from the pressure gradient balance with the downward tug of weight and the upward nudge from the moving water. A tiny equilibrium that shifts if you tilt the bottle. Tilt on purpose and watch the core bend. It will precess lazily, its base still pinned in the neck, while the top wanders under the combined pull of gravity and uneven friction. Bump the bottle and note how quickly the funnel heals, because the inflowing water keeps feeding rotation at the neck and the air core lowers resistance to outflow, so the system prefers the organized state. If you want a striking contrast, make two setups, one with a single bottle and hole in the cap to the open air, the other the two-bottle link. When you stop the swirl, the open-air bottle reverts to glug-glug immediately, while the two-bottle rig struggles because the trapped top bottle has to pull air down through the same path as the outflow, until you spin and rebuild the separate lanes. It's a crisp demonstration that venting, not just gravity, decides how fast a container drains. The same physics. Rotation creating a pressure dip along an axis runs larger, louder machines in the world. Cyclone separators in workshops and vacuums strip dust from air by spinning the mixture. Heavy particles are flung outward and slide down, while clean air escapes up the core. Wastewater plants use vortex devices to skim grit and protect pumps. Salad spinners and some oil purifiers rely on similar forced pathways to sort dents from light without delicate filters. Even storm drains and dam spillways form stable air cores that keep flow smooth and reduce violent sloshing. Real tornadoes and dust devils, of course, are born differently, by buoyant plumes, wind shear, and strong updrafts. Yet the familiar eye, the low pressure at the center, the way debris rides helical paths all rhyme with what's humming in your hands. Your bottle merely supplies the rotation directly instead of recruiting the sky. Keep the setup thoughtful and safe. Use plastic, not glass. Tape threads well so the connector doesn't leak. Mix colorants sparingly and avoid anything that will rot or clog. Don't hand the bottle to small children with the cap off. Keep caps and tiny parts out of mouths. Set a towel under the work and wipe after each run so friction at the walls stays consistent. If you want to turn beauty into gentle measurement, lay a ruler behind the bottle and film from the side. Mark how the funnel's tip drops as the water level falls and how the core diameter changes with spin strength. Time how long a fixed volume drains with and without a vortex, and let your timing tell you the scale of the improvement, almost always dramatic. Then change one thing at a time and keep a notebook. Add glycerin, and the drain slows but the funnel sharpens. Add detergent, and the funnel becomes frothy and slightly unstable. Use warm water, and the spin decays faster because lower viscosity. Gives friction at the walls more leverage. Scratch the inside lightly and feel the swirl lose elegance because roughness steals rotation quickly, a reminder that surfaces matter. When you're done chasing variations, it's worth pausing for the quiet metaphor the bottle earns. Your first, thoughtless inversion made chaos and noise, competing flows stopping each other at the doorway, while a single organized twist created a clear channel and let both directions move at once. The total effort didn't increase, but the arrangement did, and arrangement made the difference between sputter and flow. Set the bottle upright, Watch the last micro whirlpool fade to glassy calm, and carry away a firm intuition that rotation isn't only spin, it's a tool for separating paths, lowering resistance, and turning stuck systems into smooth ones. Whether your bottle is a kitchen experiment, a workshop filter, or a moment in life that needs a clean exit and a clear way in, homopolar motor, the simplest spinning electric engine. Balance a strong coin magnet under one end of a AA battery. Touch a loop of bare copper wire from the battery's top to the magnet's rim, and the wire suddenly whirs like a tiny propeller. A silent, stubborn spin that feels like you've snuck an engine out of 3 parts and a law of nature. This is the homopolar motor, the most stripped-down electric motor you can build, and its honesty is disarming. No switching, no coils to flip fields back and forth, just a steady current crossing a steady magnetic field so that each bit of moving charge feels a sideways shove, and the entire wire answers by rotating. Build it carefully and the physics becomes obvious in your hands. The battery provides a constant push for charges. The magnet supplies a constant magnetic terrain. Complete the circuit with a wire that touches the battery's positive cap and then brushes the magnet's rim, and current flows down through the wire into the magnet and back through the battery. Because parts of that current trace a path that cuts across the magnetic field near the magnet's face, the wire experiences a sideways force everywhere it crosses that region, not forward along the wire but perpendicular to both its direction and the field. Arrange the wire as an off-center loop so that shove has leverage around the battery's axis, and the result is a torque that sets the wire spinning smoothly around the magnet like a dancer who has learned exactly where to place each step. If you reverse the battery or flip the magnet, the direction flips, change either the flow or the field, and the sideways push reverses, so you can feel the rule without memorizing a gesture. Switch one thing and the spin changes. Switch both and it returns. A few craftsman tricks make the whole affair reliable and safe. Use a fresh alkaline cell or a low-drain rechargeable. Choose a small neodymium disc magnet that sticks firmly to the battery's negative end. Strip solid copper wire and polish the last millimeter that will touch the positive cap and the magnet's rim. Clean metal makes clean contact. Bend the wire into a symmetrical shape so that it can rest lightly on the cap. Sweep outward and then curve down to brush the magnet's edge. You want minimal friction and just enough contact that the current is strong but not wasteful. When you set the wire in place, it should begin to turn within a second. If it jitters or stalls, adjust the height so the brush point is exactly at the magnet's face. Where the field is strong and the leverage is good, watch for heat. The battery will warm because you're essentially creating a low resistance loop. So run the motor in short bursts, tens of seconds, not minutes. Then let things cool. Keep magnets away from credit cards and medical devices. Never leave the setup unattended on flammables. And do not short a high-capacity cell or a lithium pack, which can overheat fast. Once you have a stable spin, nudge the design into a workshop of lessons. Sculpt the wire into different profiles, wide loops, tight spirals, simple straight arms. And notice that torque grows when the current path gets farther from the axis. A long arm gives the sideways push more leverage and spins easier at the same current. Bring the brush point closer to the battery's center and the spin weakens. You've built an intuitive map of how radius multiplies the effect of a given force. Try a softer copper strand versus a stiff one. The flexible wire wiggles and vibrates as uneven contact adds and removes current, while the rigid loop glides with less chatter. Polish the contact spots with fine sandpaper and the motion becomes cleaner still, an ear-level reminder that friction and roughness convert energy into heat and noise. Flip only the magnet and watch the rotation reverse. Hold the magnet, but reverse the battery and it reverses again. That symmetry teaches you, without symbols, that what matters is the crossing, current across field, more than any single part being positive or negative. Add a second magnet stacked under the first to strengthen the field, and the spin starts more assertively. Remove it and the motor looks shy. Slide a thin steel washer between magnet and battery, and you'll distort the field into a shape that either helps or hinders depending on where the wire brushes. A tactile way to sense that fields, like wind, have direction and shape, not just strength. If the wire jerks and sticks, You're likely forcing too much contact area or pressing the loop down so hard that friction cancels the tiny torque. Lighten the touch until the wire just grazes the cap and the magnet's rim. If it still stalls, clean fingerprints from the battery top. Oils can interrupt both contact and cooling. Now that the motor behaves, widen the experiment. Replace the free spinning wire with a train style. Rest the battery horizontally across 2 rails of copper wire that run over a pair of small magnets arranged on a metal ruler, so their faces alternate north-south. The battery will roll along the rails as the same sideways force now acts on current that runs through the battery ends, giving you a linear motor. You can see a railway car powered by geometry alone, or build a Faraday disc. Press a copper coin onto the magnet's face. Connect the center of the coin to the battery top with a wire, and touch another wire from the coin's rim to the battery bottom. When current flows from center to edge across a rotating magnetic field region, the whole coin feels a torque and begins to rotate. It's less flashy but historically rich, the earliest electric motor concept distilled. Through each variant, the idea repeats faithfully. Steady electric push plus steady magnetic landscape equals steady sideways shove on moving charges. And if those charges travel along a path that wraps around an axis, the shove becomes rotation. You'll also meet the practical costs every motor designer manages. Efficiency is modest because you're shorting a source through low resistance. Heat is the price of simplicity. Brushes wear, contacts arc lightly and magnets saturate to increase torque without waste. Engineers use coils to multiply current paths, commutators or electronics to switch the push so it stays aligned, and iron cores to guide fields. Your homopolar build skips all that, trading polish for bite-sized clarity. That trade is a gift if you use it well. The motor won't lie to you with hidden mechanisms or software. It spins, or it doesn't. And when it fails, you can usually point to a single culprit. Poor contact, weak field, too much friction, drained cell, or a geometry that gives no leverage. You can even feel eddy currents, the ghost forces that oppose change. Wave a second magnet near the spinning wire and it slows without touching. Moving metal in a magnetic field makes currents that fight motion, so you get a fingertip demonstration of braking that shows up later in trains and exercise bikes. Keep notes as you tinker. Map wire shapes to startup time, magnet stacks to speed, brush pressure to heating. Film at high frame rate, and you'll see tiny oscillations at the brush point that smooth out when you reshape the loop. Add a paper collar as a thrust bearing to minimize rubbing at the battery's rim, and the motor runs cooler and longer. Shape the wire to lift gently off the cap as it spins faster, and you've built a crude governor that limits current at high speed. When you finally set the parts down, it's worth asking why this 3-piece engine feels so satisfying. It's not just the surprise of motion from stillness, it's the way the device teaches by doing. You can flip one variable at a time and witness a clean reversal or a measurable change in vigor. You can extend the principle from spin to slide and back again. You can touch cause and effect without translation. Faraday would recognize your desk, a battery, a magnet, a conductor, and curiosity. You leave with an intuition that outlives the build. If you want motion, arrange a path where the push is always sideways to it. If you want control, give that push leverage. If you want reliability, clean the interfaces where energy enters and leaves. The homopolar motor is the smallest, truest promise of electromechanics. Alignment matters more than ornament. And when you get the crossing right, even a loop of wire remembers how to dance. Lemon battery. Power an LED with fruit chemistry. Take a lemon in your palm, roll it gently on the table until it softens and the juice wakes inside. Then press a strip of bright copper into one side and a dull grey galvanized nail into the other. And notice how ordinary the picture looks, citrus and scrap metal, until you bridge the two with wires and an LED, and the tiny lamp blinks to life. It feels like a party trick, but what you've built is a real battery, a quiet factory where metal willingly lets go of its atoms and the juice carries the news. And the light is your witness that chemistry can be convinced to do work you can see. The roles are simple once you name them with your hands. The zinc on the nail is the giver. It sheds atoms as charged particles into the lemon and leaves their electrons behind in the metal. so that nail becomes the negative side. The copper is the receiver. Electrons arrive through the wire, and the lemon's acid offers them a job, helping turn charged hydrogen in the juice into harmless gas at the copper tip. So the copper becomes the positive side. Connect the long leg of a red LED to the copper and the short leg to the zinc, and the diode will glow if you've built enough push, which is why one lemon rarely does more than flicker. Its gentle voltage is usually under a volt, while a red LED wants roughly twice that. So you chain 2 or 3 lemons in series, copper of one to zinc of the next, until the lamp steadies like a cherry ember. Building is forgiving but specific. Use a real piece of copper and a zinc source. Sand both until they shine so oxide films don't block contact. Roll the lemon beforehand to break the little juice pockets so the interior becomes a better, wetter path for ions. Space the metals a finger width apart so they don't touch inside. And make your links with jumper leads or twisted wire, keeping the polarity clear. Copper to LED's long leg, zinc to the short. If the LED sulks, try a second or third lemon, or swap for a high-efficiency red that lights at a lower threshold. Whites and blues are harder guests. They demand more push than fruit politely offers. What the lemon provides isn't energy pulled from the fruit like a squeezed battery. It's a medium that lets a favored metal reaction happen and keeps the charges honest. Charged atoms drift in the juice to balance what the electrons do outside, so the whole loop can continue without building up an impossible imbalance. Taste and smell, citric acid, a pinch of dissolved salts. Make the liquid conducting enough for this migration, and you can tune that path. A sprinkle of table salt will boost conductivity and brighten the LED, but will also make the metals wear out faster. Warming the lemon a little speeds reactions modestly. Very cold fruit makes sluggish batteries. You can push beyond folklore and treat your kitchen like a lab without drowning in numbers. Build 2 identical lemon cells and wire them in parallel, and you'll feed more current to a small motor, though the voltage won't climb. Wire a chain of 3 in series and you'll get the voltage needed for most red LEDs. Measure with a cheap meter and you will see the number rise as you add lemons in series, and the available current rise as you add parallel branches. Scratch the galvanized nail after a few minutes and the brightness flicks up. Oxides and bubbles build on the metal and slow the reaction, and a fresh surface helps. Rotate the nails each hour and you'll stretch the life of your cell. Try vinegar or sports drink instead of lemon, and you'll learn that the acid or salt content matters more than the fruit's fame. If your coins don't work, it's probably because copper-colored isn't copper. Many modern coins are steel or zinc with a thin coat, and that coat can be damaged or mismatched. A bare copper wire never lies. The chemistry you're steering isn't exotic. The zinc side quietly dissolves as zinc ions, releasing electrons. The copper side offers those electrons to hydrogen in the liquid, which pairs up as bubbles that cling and then float away. If you watch closely, you'll see those tiny beads forming on copper, each popper proof that the loop is alive. If they smother the metal, stir the lemon with a gentle twist, or wipe the copper clean, because a blanket of bubbles blocks the surface, the same way foam on a pond blocks wind. There is safety worth saying out loud. Don't eat the lemon after pushing nails into it. The metals and their oxides don't belong in your mouth. Wash your hands and the table afterward. Avoid shorting the battery directly with thick wire. The lemon limits current, but the nail can still heat and stain. And keep magnets and lithium cells out of this picture entirely. This is a fruit and metals lesson, not a fire drill. Once you're confident, raise the ambition just a notch. Cut a potato and try the same build. It works differently because the chemistry inside is less acidic but still willing. Test a tomato, a kiwi, or a cup of vinegar, and learn that a liquid with ions and a taste for accepting electrons is the real requirement. Make a 4-lemon chain and power a small digital clock designed for eco kits. Then pour 1 lemon and watch the digits fade. A clear vote for voltage matters. Pair the fruit battery with a tiny buzzer and note how it chirps weakly and then brightens when you add a lemon. A sound map of what the eye already told you. If you want a cleaner current, build a salt bridge. Tear a strip of paper towel, soak it in salty water, and drape it between 2 small cups, one with zinc and lemon juice, the other with copper in the same, and connect your LED across the metals. The paper bridge ferries ions without mixing the cups. And the LED steadies, a homemade echo of how real cells are separated to guide reactions and cut losses. Think of what this teaches you beyond the glow. Metals carry different appetites for letting go of their atoms. Pair a generous giver with a willing receiver, and the space between them can turn that difference into work. The electrolyte, the lemon, doesn't push. It permits a reminder that conditions can be more important than effort. A single cell doesn't meet a threshold, but a thoughtful series does. And once you cross that threshold, a little device wakes and stays awake until the materials tire. The LED's one-way nature also nudges you to care about direction. Flip the leads and it stays dark. Not because the battery has failed, but because you asked the part to work against its grain. Respecting orientation is small but powerful learning you can feel in your fingers. When the metal's finally dull and the light dims, don't call it failure, call it closure. You have spent the zinc you offered, and that spending is why the lamp lit. Rinse the nails, compost the fruit, and write down what worked. How many lemons, which LED, how long the glow lasted, whether warmth helped, whether salt was worth the trade-off. Knowledge, like electricity, moves best in loops. And carry the quiet thought the lemon leaves on your bench. Power isn't always about size or sound. Sometimes it's a difference in willingness held gently apart by a medium that lets the conversation happen, and a patient chain that adds small pushes until a small light becomes certain. Static can race. Balloon charges push a soda can. Set an empty soda can on a smooth table. Rub a balloon briskly on your hair or a wool sweater until it crackles. Then bring the balloon within a few centimeters of the can and watch a small, bright piece of classroom theater begin. The can twitches, turns its shoulder, and rolls toward the balloon as if pulled by invisible string, keeping pace as you guide it across the table. The simplest race you can stage with electricity, you make by hand, and a crisp way to feel how charges, attraction, and friction collaborate to turn a still object into motion. The setup looks like magic until you slow your attention. Rubbing the balloon strips a tiny excess of electrons from one surface to the other, so the balloon carries a net charge while the aluminum can, a good conductor, remains neutral overall, but allows its own electrons to slide around freely. As the charged balloon approaches, the mobile electrons in the can shuffle, crowding, slightly to the far side and leaving a slight deficit nearer the balloon. So the near side of the can becomes effectively opposite in charge to the balloon and is therefore attracted. Because the can sits on a surface with a whisper of friction, that sideways pull finds traction and becomes torque. The near edge is tugged forward a hair more than the far edge. The can rotates and the center of mass steps in the direction of the pull, turning polarization into a steady roll. You can prove it's not static cling gluing things together, but a dance of charges responding to distance. Move the balloon away and the can slows. Bring it back and the can accelerates. Hold the balloon still and the can stops beneath it instead of leaping up to stick. Because gravity and the table conspire to keep the can grounded, while the net sideways force requires your misalignment to make a roll. Humidity is a quiet referee here. On a damp day, water in the air and on surfaces leaks charge away quickly, dulling the effect. On a crisp, dry day, the balloon keeps its extra electrons longer and the can darts with a confidence that makes kids grin. If the show feels weak, dry the room a little or switch to a grabbier pair like latex and wool or PVC and fleece. Now tune the race like an engineer. A full can is sluggish, it's heavier, and friction that once helped now demands more pull for the same turn, while an empty can glides. A crushed can has a lower contact area and sometimes skitters rather than rolls because friction can't deliver even torque. Rough tabletops bite too hard and trap the can, while glassy ones offer so little grip that the can slides sideways without turning. A sheet of printer paper on a kitchen table often hits the sweet spot. Cleanliness matters more than pride. Skin oil and dust reduce both charging and contact, so wipe the balloon and the table with a dry cloth, and keep your fingertips off the charge patch once you've rubbed it up. You can get quantitative without spoiling the fun. Mark start and finish lines. Time a series of runs at fixed balloon can distances, or tape a protractor to the table edge to hold your hand at a constant angle. Compare wool versus cotton, latex versus plastic pipe, cool room versus warm, and let the can be a meter that reports how long the balloon's charge lasts under each condition. Replace the balloon with a charged plastic comb and the race still works, confirming that it's the charge, not the balloon's material, that matters. Replace the aluminum can with a plastic bottle and the response shrinks, because plastic's charges don't rearrange internally the way a conductor's do. Your first quiet lesson in how conductors and insulators answer fields differently. If you're feeling bold, let the can touch the balloon for an instant. Sometimes, after contact, the can picks up a bit of the balloon's charge and then briefly repels, refusing to follow until the charge leaks away to the air or to your hand. An honest demonstration that attraction comes first from polarization, while repulsion requires like charges on both objects. You can also ground the can with a fingertip and feel the tug grow. By giving the can a place to offload excess charge, you strengthen the polarization and the forward pull, but do it lightly. Too much contact turns your body into a giant lightning rod that collapses the delicate separation you just built. For a visual of what your hands already sense, tape a thin thread to the can's near side. As you move the balloon, the thread swings toward it, showing the hidden sideways force. Swap in a strip of tissue and the paper itself jumps to the balloon, proving that polarization pulls on insulators too, only with less drama than on a metal. If the can's behavior seems moody, remember that charge is a soft currency. It migrates along humid films, vanishes into the air, and pools at microscopic bumps. Repeat a run after a pause, and you'll sometimes get a faster start because the can's electrons have had time to spread to their favored arrangement again. Rub the balloon longer, and you may see diminishing returns because the surface already holds about as much extra charge as it can without leakage. Safety is simple. Avoid rubbing near open flames or solvents. Keep long hair and loose clothes away from candles, and don't go hunting shocks. This is a low-energy demo designed for gentle curiosity. Once you find the rhythm, push the idea further without repeating yourself. Make 2 tracks side by side and race 2 cans with 1 balloon, noticing how a tiny difference in can mass or surface friction crowns a winner. Elevate one edge of the track by a book and test whether the can can climb a shallow slope under the balloon's lead. Tape a tiny square of aluminum foil to the can and see if the shiny patch changes how readily it responds. Hold the balloon behind a thin pane of glass and discover the can still follows. Fields cross the insulator easily while charges do not, teaching you that influence doesn't always require exchange. The world is full of echoes of this tabletop lesson. Photocopiers and laser printers arrange toner with electric fields and then fix it with heat. Electrostatic precipitators pull particulates from smokestacks. Air filters boost capture with charged fibers. Paint shops use fields to coax spray into an even coat. Even grain silos take static seriously, controlling charge to prevent dangerous sparks. Back at the table, the clearest thought to carry with you is that motion here isn't about pushing the can from behind. It's about creating a difference in the space around it that the can cannot ignore, then letting friction translate that quiet bias into a roll. When you finally lift the balloon and the can settles, the room looks unchanged, but you've gained a felt map of cause and effect. Rub, bring close. Watch charges reorganize. See attraction become torque. Adjust distance, watch speed change, feel humidity matter, and note how a moment of contact flips the story for a breath. That's more than a party trick. It's a discipline. Learn to set conditions that make the path of least resistance point where you want to go, and small, nearly invisible forces will do surprising amounts of work, with your hand only nudging the air. Magnet in copper pipe. Slow fall via eddy currents. Hold a copper pipe upright. Drop a strong neodymium magnet into the mouth, and brace yourself for a small shock to your intuition. Instead of clinking out the bottom in a blink like a coin or a marble, the magnet drifts, calm, deliberate, almost polite, taking a lazy second or two to emerge as if the pipe had turned into syrup. Yet copper isn't magnetic and you didn't add any brakes, so what slowed it? The answer lives in motion and response. As the magnet's field sweeps past the copper's atoms, It nudges the pipe's free electrons into loops, eddy currents, that whirl inside the metal like tiny racetracks. Those currents create their own magnetic fields that oppose the change that birthed them. So when the magnet tries to fall faster, the eddies push back harder, and when it moves slower, they ease off, automatically tuning the drag to the speed and turning the fall into a soft negotiation rather than a crash. You can feel the logic with simple comparisons before you name anything. Drop the same magnet through a plastic or cardboard tube and it rockets down. No free electrons, no eddies, no break. Switch to an aluminum pipe and the slowdown returns, sometimes nearly as strong as copper's, because aluminum's electrons run freely too. Try a steel pipe and you get a different story entirely. The magnet may stick or bounce oddly because steel is ferromagnetic, so static attraction and domain physics get in the way of the pure eddy current tail. Copper is special here because it's an excellent conductor but not magnetic, so it supplies the cleanest stage for the moving field drama. Tinker without fear and the details bloom into lessons you can keep. Stack 2 magnets and the descent slows further. The stronger field drives more robust eddies, which push back more. Flip the stack end over end and the timing hardly changes because the pipe doesn't care which pole leads, only that the field is marching by. Warm the pipe in your hands and the fall becomes a touch slower because hotter copper conducts a little worse, squandering some of the eddy's effort as heat. Chill it and the magnet speeds up. Colder copper conducts better, so currents circulate more efficiently and paradoxically reduce the energy lost to heating at a given speed, which lets the magnet find a slightly higher terminal speed where the drag balances weight. Now cut a narrow slit down the pipe, carefully on a sacrificial scrap, and repeat. The slowdown collapses, and the magnet zips through because the slit breaks the loops that eddy currents need to circulate. Tape the slit closed with conductive foil, and the break returns, a striking, handheld proof that the currents really are loops, and that continuity matters more than thickness past a point. Thickness does matter though. A very thin-walled pipe caps the size of the whirling currents and softens the effect, while a thicker wall gives them room to spread and strengthens the break, up to a practical limit where more metal just adds weight, not much extra pathway. If you want to see the invisible made visible, drop the magnet while you hold a sensitive compass beside the pipe and watch the needle wiggle as the traveling eddies and the magnet's field sweep by. Touch the pipe after a long series of drops and it may feel faintly warm. The kinetic energy that didn't become speed becomes heat, a tiny tax paid by the eddies for doing their job. A few honest gotchas keep the story clean. Don't let the magnet graze the wall. Friction and nicks will masquerade as physics. Keep fingers clear of stacked neodymiums. They pinch hard. Avoid pacemakers and magnetic strips. And never treat glass as a substitute tube. If the magnet catches an edge or the pipe chips, you've traded learning for sweeping. Once the basic effect is solid in your hands, map out how speed self-selects. If you film the fall against a ruler, you'll see the magnet accelerate at first, then settle into a steady descent. Terminal velocity, because the eddy current drag grows with speed until it equals the pull of weight. Heavier magnets with the same size tend to fall faster because gravity asks more of the eddies, and they answer by allowing a higher cruise speed before balance. Larger diameter pipes reduce the break because the magnet's field fades with distance, so the wall's electrons feel a weaker shove. A tight fit amplifies things because the field at the wall is stronger and changes rapidly as the magnet passes. Try a ring magnet that's slightly wider than the pipe's inner diameter, and the show becomes dramatic. The ring's field couples strongly to the wall, and the descent can stretch to a slow-motion crawl. Switch to a tiny button magnet in a huge pipe, and you'll barely notice anything. It's a dance, not a law carved in stone, and coupling decides the steps. You can push the idea sideways into devices you meet in the world without repeating a single kitchen trick. Roller coasters use eddy current brakes, rows of copper fins and permanent magnets to give reliable, fail-safe slowing. No electricity required, no moving parts to seize. If the car speeds up, drag grows. If it slows, drag relaxes. Self-correcting calm at thrilling scale. Induction cooktops heat pans by driving eddy currents in the cookware, turning metal into its own heater. Metal detectors sniff those currents and their magnetic fingerprints to decide what lies underground. Coin sorters and recycling plants fire pieces of metal off conveyor belts with spinning magnet drums that pump eddies into conductive bits, repelling them smartly into collection bins. High-speed trains and exercise bikes use similar non-contact brakes to convert motion to heat without friction pads that wear. To underscore how non-magnetic metal slows a magnet is not a contradiction but a coherent rule. Hover a magnet over a thick, flat copper plate and give it a gentle horizontal push. It slides but reluctantly, as eddies bloom under the moving field and push back against the change. Now chop shallow slots in the plate, and the resistance fades along those cuts. Again, loops need continuity. If you want a no-words picture that lodge in memory, hold a small aluminum ring above a coil hooked to AC power and switch on. The changing field beneath the ring induces currents that make the ring leap upward. Switch to a slotted ring and it barely stirs. The same loop logic dressed in a different demo. What this episode leaves in your hands is a feel for how systems can resist change without contact, how nothing touched it doesn't mean nothing acted, and how creating paths for reactions, in this case, electrical loops, determines whether energy becomes motion or warmth. The magnet took longer to fall, not because copper grabbed it, but because copper allowed currents to organize in a way that pushed back exactly as much as needed to keep the story smooth. Cut the loops and you cut the break. Strengthen the loops and you get a gentle glide where your instincts expected a clatter. When you finally let the last magnet clack onto the table and the pipe cools in your grip, you'll have a quiet new habit, looking for the hidden loops in other problems, the paths that let a system write its own opposition to sudden change. And that's a kind of seeing that outlasts any single drop. Crush a can with air pressure, hot-cold flip demo. Set a spoonful of water in an empty soda can. Hold it with tongs over a stove or hot plate until the inside sings and white plumes curl from the mouth. Then flip the can mouth down into a shallow bowl of icy water and listen for the startled gasp of metal. The can crumples inward in a single, decisive beat, as if an invisible hand squeezed it. Nothing supernatural happened, only a quick change of who's pushing whom, and once you learn to read that flip, you'll never look at air as empty again. While the can heats, the tiny puddle inside boils and fills the can with hot water vapor, driving most of the ordinary air out the top. That vapor is just water in another mood, spaced out, energetic, crowding the interior, and it keeps the can's pressure roughly matched to the air outside because the mouth is still open. The drama begins when you invert the can into the cold bath. The mouth seals against water. The vapor trapped inside touches chill, and in a blink, it condenses back to liquid on the can's inner walls. That phase change is not just a costume swap, it erases volume. Gas occupies hundreds of times more space than the same amount of liquid. So when vapor collapses to droplets, the interior suddenly holds far fewer gas molecules than before. Outside though, the atmosphere hasn't changed its mind. The air around the bowl still pushes with the same patient weight it always carries. A tall stack of sky pressing on every surface. With the mouth now underwater and the inside short on gas, pressure inside dips well below pressure outside, and the result is a net push inward from all directions. Aluminum is strong for its mass but thin, and the walls fold along their weakest ribs with a noise that reminds you, pressure is a force you can only ignore when it's balanced. You can prove to yourself that it's the outside doing the work, and not suction inside, by repeating the demo with the can tipped, so a tiny straw holds the mouth just above water. As soon as air can sneak in, the crush vanishes, the interior refills, pressures even out, and the can survives. Remove that breath line, and the next condensing wave pulls the inside low again, and the walls surrender. Tune the setup, and the story grows even sharper without ever needing a cymbal. Use a few ice cubes in the bowl to bring the water well below room temperature, and the implosion becomes crisp, because colder surfaces pull vapor back to liquid faster. Linger too long on the heat and the can's paint may smoke or the metal soften, making the collapse messier. So watch for steady steam and act. If you try warm tap water instead of ice, the crush still works but slows, and the can sometimes dimples before committing. Your first feel for how rates compete. Choose a can with well-defined ribs, and you'll get a clean fold ridge to ridge. Pick a stout soup can, and you'll need more vapor and a colder bath to see it buckle. Step up to a large, empty metal gallon can. Pour in a cup of boiling water, cap it tightly, and set it in a sink under cool running water. The sides pull inward with a deep creak that feels like the air is finally introducing itself. Loosen the cap, and the walls spring back a little as the hidden pusher, the surrounding atmosphere, loses its advantage. If anyone nearby insists the can is sucked in, you can suggest a kinder description. The can is crushed because the room refused to relax while the inside lost support. Air doesn't need drama to be powerful. At sea level, the stack of sky above each square of surface weighs about as much as a loaded hardcover pressing down on your palm, and a can carries many such squares. We usually forget because the push is equal in all directions, and our bodies are filled with fluids that push back from within. The demo works by breaking that tie. Small details matter if you want reliable results and a safe bench. Use tongs or pliers whose jaws hold the can under the rim, not squeezing the sides. Wear eye protection. Keep sleeves clear of flame. Never hover your face over the mouth of a steaming can. Use only a spoonful of water. More simply slows the heating. Set the bowl on a stable surface and leave space to move. If you have an induction cooktop or a hot plate, the process is calmer than over an open flame. If you have neither, you can start with a can that already has boiling water inside, poured from a kettle. Swirl it for 10 seconds to fill the interior with steam. Then invert. Quick hands make the difference. To turn theatre into understanding, vary one thing at a time. Try different mouth seals. Dunk straight down for a quick crush, or tilt so a bubble of trapped air remains and the collapse is partial. Tape a temperature probe to the outside and note how little the wall itself needs to cool before the effect triggers. The vapor is the key. Time the delay between dunk and crunch with and without ice, and discover that the crush waits for condensation to remove support, not for the metal to freeze. Hear the soft glug as water is sucked a centimeter up into the can as the sides fold. Another sign that the interior pressure fell and the outside surged. Failures when they arrive are teachers disguised as quiet cans. If nothing happens, you likely didn't purge enough air before the dunk, not enough steam inside. The bath wasn't cold enough, condensation too slow, or the mouth wasn't sealed, outside air slipped in to level things. Fix each in turn. Wait for a strong, steady plume before inverting. Add ice. Submerge decisively. You can invert the logic for a cousin demo that won't borrow from earlier topics. Set a balloon over the mouth of a flask, then heat or cool the flask to watch the balloon sag in or puff out. Not because the balloon decided anything, but because the inside pressure fell or rose with temperature changes and phase changes of the little water trapped within. Out in the world, the can crush intuition scales everywhere. Tanker trucks can crumple under a cold rain if a steam cleaning leaves them sealed with hot, humid air inside. As the vapor condenses, the outside air pushes the huge panels inward like paper. Sealed Regent bottles dimple when cooled too quickly. Weather gives us a daily map of pressure pushes. Highs bring sinking air and calmer skies. Lows lift and swirl. And your ears sense those changes on a plane descent as a gentle ache that clears with a yawn, because your body needs to equalize inside to meet outside. The demo also pushes on thinking. Nothing touched the can from the outside. No hands, no clamps. Yet the more decisive force came from there. The lever was a change inside that let an environment reveal itself. To close the loop cleanly, do one last trial and then pause. Heat. Watch for steady steam. Invert with care. Hear the crisp crinkle. Feel the quiet power of air you usually ignore. Then give the can back its support. Lift it, tilt the mouth above water, and listen as a breath of room air rushes in and the walls relax a notch. The lesson doesn't need numbers to stick. Balance pressure and nothing moves. Remove support on one side and everything answers. Most of the world is held up by ties we don't see until they break. When you wipe the counter and let the last can dry, you leave with more than a party trick. You carry a tactile memory that emptiness isn't empty, that the space around you is an active partner applying gentle, constant force, and that small changes at the boundary can flip who's in charge, turning the quiet weight of air into a hand strong enough to fold metal. Cloud in a bottle, pressure drop condenses mist. Cap a clear, sturdy bottle. Pump a few strokes of air into it with a snug stopper, and then snap the valve open just a crack. The air inside sighs, the temperature dips in an instant, and a soft white mist blooms from nothing like a genie changing its mind. A tiny weather system that appears and fades on your command and teaches you that clouds are not made of cold air, but of countless tiny droplets that form when warm. Moist air is cooled past its comfort point faster than it can adjust. The secret is a quick pressure drop that makes the air expand and cool, lowering the amount of water vapor it can safely hold before excess condenses on whatever microscopic specks are available. Do the kitchen version carefully, and you'll feel every step in your hands. Use a thick plastic bottle that can take pressure. A small soda bottle works. Fit a rubber stopper with a bike valve adapter, and add the most important ingredient after water vapor: nuclei. The tiny surfaces droplets need to start by lighting a short wooden match, blowing it out, wafting the faint smoke into the bottle, and capping it quickly. Now pump a few strokes to raise the pressure, which warms the air slightly. Then release the valve with a quick twist and watch the contents flash white, because the sudden expansion cools the air, and the vapor that was comfortable a moment ago finds it no longer has enough space to remain invisible. If you prefer an all-plastic no-match approach, put a thimbleful of rubbing alcohol in the bottle, cap loosely, and shake for a few seconds so vapor fills the space. Alcohol evaporates easily and provides plenty of molecules ready to condense. Then squeeze and release the bottle with your palms. Each squeeze raises pressure and temperature and clears the view, and each release lets the air expand and cool, so a ghostly cloud returns. The on-off nature is the whole point, because it proves the fog is not dust alone, but droplets that appear when conditions cross a threshold and vanish when they retreat. You don't need to memorize names to understand what you're seeing, but the picture sharpens when you notice 3 levers you control: moisture, temperature, and nuclei. Moisture is the supply of invisible vapor ready to join a droplet. Temperature sets how much vapor air can keep hidden before it spills out as mist. Nuclei are the scaffolds that let the first droplets form at ordinary temperatures, because perfectly pure air resists starting a droplet without a surface. When you pump, you warm and concentrate the air, and when you vent, you let it expand and cool so quickly that it overshoots its comfortable balance and condenses on the smoke or alcohol haze you provided. Failures teach as cleanly as successes. If no cloud appears, you probably skip the nuclei, repeat with a wisp of smoke, or use the alcohol method. If the bottle fogs instantly and stays that way, you likely vented too far and moisture condensed on the walls instead of as floating droplets. If the show is dull on a humid day, paradoxically, you may have plenty of vapor, but too few nuclei. Modern indoor air is surprisingly clean, so add a trace of smoke. If the bottle feels floppy and lifeless, use a fresher, heavier bottle so the pressure swings are real. Once you have a reliable cloud, turn the prop into a lens on outdoor weather without reusing any old tricks from other topics. Squeeze and hold to compress and warm your air parcel and the cloud clears. Then release and let it rise and expand, and the cloud returns. The same balancing act plays out when real air climbs the side of a mountain, when a parcel is forced over a cold front, or when evening cooling lets fog walk ashore. Carry the bottle to a window on a warm, damp day, and you'll appreciate why your breath sometimes turns visible in winter. The air you exhale is moist and warm, but a sudden meeting with cold outdoor air pulls it past its comfort line, and droplets form for a moment on the dust that is everywhere. Watch carefully and you'll see the mist is not uniform. Near the cap, where the pressure drop is strongest, the cloud appears first and thickest, and then gravity, gentle and patient, makes the densest droplets settle while the rest hang and swirl. Shine a flashlight through the bottle from the side, and the beam outlines tiny bright specks that drift and merge, the way real cloud droplets grow in stages, from tiny seeds into larger drops through collision and collection, long before rain is possible. If you want to feel how rhythm matters, make small, Rapid pressure taps. A quick flick produces a faint veil. A deeper vent gives a brilliant bloom. And holding the vent open too long kills the act because you stop giving the air a chance to rebound. Clouds live on differences, not on steady sameness. Safety is simple and non-negotiable. Use plastic, never glass. Don't overpressurize. The point is a few firm strokes, not a science fair cannon. Keep flames away from alcohol vapor. If you use matches, let the ember die before you bring it near the bottle. Wear glasses if you have them, and keep curious faces back as you learn your bottle's limits. When the mechanics are comfortable, test variations that turn curiosity into understanding more durable than any one demonstration. Swap smoke types, match smoke, candle blown out, a smear of chalk dust, and compare which makes the crispest cloud, learning that not all nuclei are equal. Try a tiny splash of hot tap water instead of alcohol, and notice you get a decent show, but with shorter-lived bursts, because water vapor needs a slightly stronger cool down to condense. Use a colored background and watch how the mist scatters bluish light more strongly than red. A miniature hint at why the sky is bright and why distant mountains look washed in blue. Take the bottle to a cool porch and repeat. The same pressure drop now produces a denser cloud, because the whole baseline has shifted colder, pushing your parcel past its comfort point more easily. The bottle also lets you probe a question people often carry quietly. Are clouds just floating piles of steam? And if so, why don't they fall at once? Your model answers kindly. Clouds are not steam, which is invisible. They are droplets and tiny ice crystals that are small enough for air to support as they swirl and ride updrafts. And they persist as long as new cooling replaces the droplets that evaporate. In the bottle, the cloud lingers for a beat while the air is still cool, then thins as the parcel warms back up and the droplets evaporate, and you reset the cycle with another squeeze and release. You can connect this to honest, visible lines in the sky without borrowing any previous material. The white plumes from jet engines happen because hot exhaust adds water vapor to a frigid, low-pressure path where air cannot hide that much vapor, so it condenses into trails. Sometimes the trails bloom into sheets when background conditions are already on the edge. The same way your bottle makes a brighter cloud when the room is cool, and you can nod to the subtlety of nature. Sometimes outdoor air is so clean that clouds need a nudge from salt spray over oceans or dust from deserts to get started. Your bottle agreed when it preferred smoke. End by turning the prop into a small discipline of attention rather than a stunt. Set everything down. Notice how the mist obeyed your timing and your thresholds. Remember that the cloud did not appear because you made water. It appeared because you briefly changed the balance between what the air could carry invisibly and what it had to show, and hold on to the practical thought that many systems work this way. Quiet until a small drop in pressure or temperature pushes them past a line, then suddenly visible, then quiet again when the line is crossed back. When the last puff fades and the bottle returns to transparent, you haven't lost the cloud. You've gained a way to read the sky in your experiments that doesn't need symbols, only a sense for when conditions tip, and how quickly a hidden possibility can become a seen thing when pressure gives it permission. Capillary tie-dye. Paper pulls colors uphill. Clip a fresh strip of plain coffee filter to a chopstick. Scallop its lower edge with quick half-moon cuts, and lower only those scallops into a saucer of clear water, while a row of bright washable markers waits above the liquid line. Within a minute, you'll see narrow ladders of color creep upward, weave around the cutouts, and bloom into halos that feel hand-painted. Yet no brush touched the page. What's moving is not the ink by itself, but water dragging dissolved dyes through a forest of tiny passages between cellulose fibers. And the pull comes from a simple preference. Water would rather hug the fiber walls than fall back down. So it climbs, and as it does, it ferries color until evaporation slows the stream and the pigments decide where to settle. You can turn this into capillary tie-dye that actually explains itself if you treat the paper like terrain and the liquid like a traveler with choices. Start by marking small dots of different colors 6 or 7 millimeters above the bottom. Leave a clean gap so the dots don't dip directly. When the waterfront arrives, each dot dissolves into the moving wave and stretches upward into a soft comet tail that keeps its own pace. Some components lag because they grab the cellulose harder, Others shoot ahead because they prefer the water more than the fiber, writing a barcode that says, this color. Wasn't one color at all. Cut 3 strips from the same sheet, but flip 190 degrees and you'll feel the mill's hidden grain. Fibers on many papers tend to align, so wicking is faster along the lay and slower across it. The along the grain strip grows taller bands in the same time, while the cross grain one paints tighter, denser strokes. The first hint that structure you can't see still decides your picture. Trim the lower edge of a 4th strip into long, thin tines and watch those slender tongues outpace the rest, because narrower gaps pull harder. Join 2 tines with a tiny bridge of paper, and the fronts merge into a leaf-shaped pool that deepens at the seam. A quiet map of how paths meet and share flow. You can sculpt the flow without ink at all. Take a white crayon and scribble a faint star near the bottom before dipping. Wax refuses water, so the rising front splits around the invisible lines and reunites on the far side, printing a pale star with darker arms. No dye stayed where the river couldn't go. Fold the strip in a tight accordion. Press it under a book for a minute, then unfold and dip. The creases are compressed forests, slower channels, and the color writes topographic contour lines that mirror every fold. A paper version of how sediment fans form downstream of ridges. Swap pure water for a mix, say 9 spoonfuls of water and 1 of isopropyl alcohol, and the front speeds up, the edges blur, and some dyes that clung before now glide through, because the solvent blend changed what the pigments prefer. Touch a toothpick dipped in a drop of dish soap to just one corner of the dipping edge, and a single racing lane shoots ahead, then evens out. An honest hint that lowering surface tension locally makes the front surge until the difference dies. Temperature is a dial you can feel without numbers. Warm the saucer in your hands, and the bands rise taller and wider, because evaporation lifts from the top faster, quietly pulling the column upward. Chill the saucer and the front climbs more slowly but paints sharper boundaries. Raise a small desk fan and the patterns widen into feathery veils, because faster evaporation at the top tugs harder, speeding flow and thinning color. If you want tie-dye that reads like a lesson, sprinkle a mere pinch of table salt on half the strip before dipping. Irons make water more comfortable with cellulose, so the salted half often darkens and tightens, while the plain half stays airy. 1 sheet, 2 attitudes. Dust a faint track of cornstarch across another strip, and capillary force weakens there. Starch soaks water, but gums channels, so the front hesitates and your banding breaks like a shoreline around a sandbar. For bolder shapes, dab tiny circles of school glue, let them dry clear, then dip. The glue swells and turns those dots into no-go islands that shunt color into rings, which thicken as the river wraps and wraps. A paper petri dish, minus the lab. Nothing here is guesswork once you watch a whole run from the side with a flashlight. Just ahead of the advance is a damp halo, where fibers are wetted but not yet flowing. When the sharp front arrives, color surges, then thins as water evaporates and leaves dye behind. Near the top, faint tide marks appear, where the front paused. Capillary pull-up balances evaporation down until a fresh feed arrives, so the strip records its own rhythm like a tree rings its years. Failures translate directly into fixes. If the colors smudge into a muddy slab, your dot was too big or sat too low. Make it smaller and keep that dry gap so the water does the lifting. If nothing climbs, your strip is touching the saucer wall, wicking sideways, or the paper has a sizing that resists wetting. Switch to a coffee filter, lab filter, or uncoated sketch paper. If the bands streak, oil from fingers or lotion makes patchy wetting. Handle by the edges or wear a glove. If a single dye floods the whole strip, your solvent is too aggressive. Return to pure water or cool it and try again. To show that this isn't merely craft, borrow a trick from test kits. Cut a sideways branch into the strip so 2 tongues rise. Dot blue on the left tongue and yellow on the right. As the fronts meet, they mix into green only after the water brings them together, proving that location and timing decide outcomes as much as ingredients. Elevate 1 jar so the strip climbs into a second reservoir at a slightly higher level and watch a new lateral front takeoff The flow will turn and run uphill along the paper because the capillary pull in fresh fibers is stronger than gravity on such tiny columns. Tape a millimeter scale behind the strip. Snap photos every minute, and you'll discover a simple habit. In the early run, height grows quickly, then slows as the path lengthens and evaporation fights back. A feelable law without symbols that artists exploit when they wet a page to pull washes. Let the project connect to living things without repeating any earlier analogy. Slice the end of celery at a bias, dip it in dyed water, and you'll see distinct threads carry color in narrow highways that ignore nearby tissue. Because plants, like paper, are built from aligned capillaries. Now cut across and the dye prints a polka dot constellation where tubes were severed. Return to paper and draw a loose spiral of wax. Then dip. The front wraps the spiral like surf around a jetty and paints a nautilus you didn't sketch with pigment at all. Keep the table safe and the chemistry calm. Stick to food dyes or washable markers. If you add alcohol, open a window and keep flames away. Place everything on a tray. Wash hands and surfaces. Label any small bottles. Don't pour pigment-heavy water into a sink that clogs. When the strips dry, mount them in sequence. Straight edge, scallop, tine, wax star, folded topography, salted half, glued islands, solvent blend. Beneath each, jot what you changed and what it did. Narrow channels, taller climb, softer fades, salted side, deeper, tighter bands, warm air plus fan, feathery breadth. You'll have art that explains itself and a tactile model for reading real stains. From the dark rims of a coffee ring, solvent outran solids, leaving pigment at the edge, to the way rain soaks a sleeve along the yarns, flow follows structure, to how a paper test strip can decide a diagnosis with nothing but wicking and chemistry. The soft, portable insight is this: you didn't push pigment uphill with force. You offered pathways and let preferences do the rest. Waters pull along small places, fibers quiet invitation, pigments differing loyalties, evaporation's patient tug downward, and by shaping edges, grain, and timing you steered an invisible negotiation into a visible design. When you lift the last strip and it rustles under your fingers, you'll see more than pretty gradients. You'll see a record of choices made by a liquid that loves to climb, written on a landscape that learned to guide it. Marker chromatography, split hidden ink components. Draw a fat dot with a black washable marker near the bottom of a strip of coffee filter. Lower only the blank end into a shallow dish of water and hold still as the quiet betrayal unfolds. The dot that looked like a single color loosens its grip, dissolves into a traveling halo, and then splits into marching bands of blues, greens, violets, and occasionally a hard-to-believe bright yellow, a confession that what you called black was a coalition, and that with the right encouragement, those partners prefer to travel at different speeds. This is paper chromatography, the gentlest of separations, and you don't need any equations to understand it if you let your eyes do the bookkeeping. A solvent creeps up the paper by itself, the ink's ingredients hitch rides. And because each ingredient likes the moving liquid and the paper's fibers by different amounts, some are carried far while others stall and smear, so distance becomes identity writ in color. Set up with a few precise habits and the demonstration becomes an instrument. Cut strips 2 centimeters wide and 12-15 centimeters long. With a pencil, never a pen, draw a light baseline about 1.5 centimeters from the bottom and place a pinpoint dot of ink right on that line. Small is crucial, the size of a grain of rice, because a big blob simply muddies itself. Pour a centimeter of clean water into a glass, hang the strip from a clip so the bottom edge just touches the pool, and make sure the dot sits above the liquid. Cover the glass with a plate to slow evaporation, then watch the pale solvent front climb. When it reaches halfway, you'll notice the first signs of discrimination. One hue drifts ahead, another trails, a third hardly moves, leaving behind a faint ghost at the start. Stop the run when the wet front approaches the top. Pencil a quick mark where it ended, remove the strip, and let it dry. Suddenly you own a fingerprint of that ink's recipe, made with nothing but patience and a kitchen shelf. Now vary the world and read its replies. Try a different black. Some brands lean on blue, green, and purple. Others hide oranges and reds. A permanent marker refuses water almost entirely and only grudgingly bleeds a dull halo. But when you swap in isopropyl alcohol or acetone from nail polish remover, used in a ventilated room and away from flame, the permanent ink bursts open into sharp, exotic bands because the solvent finally speaks the dye's language. Washable markers go the other way. Water yields crisp ladders of their cheerful components, while alcohol smears them because it blunts the subtle tug-of-war between dye and paper. Test brown and green too. Many are not single dyes, but mixtures tuned for a mood, and the strip will tell you which ingredients the brand chose. Paper is not neutral. Coffee filters and lab filter paper wick quickly and keep bands tidy, while paper towels drink like sponges and blur edges, and glossy printer paper refuses to cooperate because a sizing layer keeps liquid on the surface. Even the direction matters. Turn a strip 90 degrees and you'll see slower, tighter bands as the solvent fights across the paper's hidden grain. Timing and weather leave their signatures as well. On a dry, warm day, the front gallops and bands spread wider because evaporation helps pull solvent upward, while in humid air the climb lingers and hues compress into narrower steps. If your bands bleed together, your dot was too big or dipped into the liquid. Leave a clean gap between spot and pool so the solvent, not the bath, does the dissolving. To make the method feel like more than a party trick, push into comparisons you can defend. Spot two different black markers on the same baseline a centimeter apart. Run them together, and you'll see how one black masks a teal and lemon duet, while another carries a violet and rust pair. Now spot the same black twice on one strip, once small, once large, and learn why analysts insist on tiny, concentrated spots. The compact one gives crisp, separable bands, while the big one shouts over its neighbors. Take a photograph beside a ruler as soon as you stop the run and note how far each band traveled relative to the solvent front. Without writing any fraction, you've built a ratio. Your future self can compare when you test the same pen a week later. Once you've felt the basic separation, you can level up without leaving the kitchen. Do a two-step orthogonal run. After the first run dries, rotate the strip 90 degrees. Place a new dot of the same ink at the fresh baseline and run it in a new solvent. Say, water first, then a touch of alcohol. Components that refuse to leave their neighbors in water often part ways in the second step, revealing that separation is about preference, not force, and that preferences change when the liquid does. Try a descending setup. Tape the top of a long strip to a ruler laid across a tall jar so the strip hangs down into the jar's air. Then wick solvent through a small paper wick at the top and let it drip onto the strip. Gravity helps you push the front through more slowly and steadily, yielding narrower bands you can measure with confidence. If you'd like to watch the moment of betrayal in higher contrast, shine a flashlight from behind as the front climbs. Just at the edge, you'll see a shimmering boundary where dye molecules unhook from the paper, ride the liquid for a few millimeters, then snap back. Those tiny decisions, made trillions of times, are what become the strokes you can point to with a pencil. Safety here is friendly, but real. Work with water first. Keep alcohols capped and away from flame. Ventilate if you use acetone, label jars. Avoid breathing close to solvent vapors, and wash hands at the end. Dispose of solvent-damp strips in the trash, not the sink. Sometimes the strip refuses to tell a story. Learn from that too. If all you see is a single stubborn streak, the dye might truly be a single component, or your solvent is a poor match. Try a blend, a spoon of alcohol in a cup of water, or warm the room a notch. If the ink sprints with the front and never separates, shorten the run or switch to a paper with tighter pores. If components refuse to leave the start, pre-wet the paper very lightly with your solvent vapor by covering the jar for a minute before dipping, then try again. This isn't just craft, it's the cleanest introduction to how chemists, biologists, and conservators ask questions about mixtures. Museums use similar logic on fragments of pigment to identify what a restorer added versus what's original. Environmental kits wick river water and leave colored bands that report on nitrates or metals. Food labs tease apart flavorings to check claims. Sports regulators test supplements, and crime labs, with more disciplined materials, compare pen inks and dyes in fibers to place a page, a check, or a shirt in context. You can even peek at the logic behind those quick medical strips that turn colors in sequence. Each lane carries a reagent anchored to the paper. A drop travels, meets zones that react one after the other, and the distances and shades become answers. If you want a closing experiment that feels like a thought you can hold, draw two identical dots of the same black on one baseline, run them halfway, stop and dry, then touch a fingertip lightly above one dot and run again. The moisture and oils you left will disturb the balance where you touched, and the second run's bands will warp, proof that tiny, local changes in the paper's personality direct outcomes you might have blamed on bad ink. End the session by laying your strips in order: water versus alcohol, different papers, warm versus cool runs, single step versus two-step, and give each a small caption: blue outran yellow, streaking fixed by smaller dot, permanent split only in alcohol, grain with against, two-step revealed hidden violet. You'll have made a gallery that doubles as a quiet curriculum. Mixtures are more common than singles. Identity can be drawn in distance, conditions select behavior, and clarity comes not from pushing harder, but from choosing the right path for a part to show what it prefers. The next time a pen writes black on a page, you'll know that a coalition is calling itself one thing, and that with a strip of paper, a shallow dish, and a little patience, you can ask it to introduce its members, one band at a time. Red-cabbage pH painter, acids versus bases in color. Slice a handful of red cabbage into ribbons, cover them with hot water in a clear jar, and watch as the leaves sigh their color into the liquid. Purple at first, then a deeper wine, until the jar holds what looks like ink pulled from twilight. When it cools, dip a brush and touch the pigment to white paper, and you're holding a paint that tells the truth about the world. This is a pH painter, a natural indicator made of plant dyes called anthocyanins that change structure with acidity. So the same stroke shifts from crimson to violet to blue to green depending on what it meets, letting you make pictures that double as chemistry maps without a single equation. Set up a simple studio and start with honesty. Pour a little of the extract into small cups and label them vinegar, lemon juice, club soda, plain water, baking soda solution, and a drop of liquid soap. Dip a strip of coffee filter into each and lay them side by side. Vinegar's patch runs ruby. Lemon slips toward bright magenta. Club soda leans pink because dissolved carbon dioxide makes it mildly acidic. Plain water settles near purple. Baking soda moves into soft blue-green. And many soaps push green toward teal because they're a bit basic. If you tip a trace of household ammonia into a separate cup, use ventilation and a light hand, the color jumps to greenish yellow, a clear warning that basic can be gentle or strong. The pattern is not magic and not random. In sour conditions, the dye's shape favors red. In balanced conditions, it prefers purple. As the liquid turns basic, the dye rearranges again and the reflected color slides into blue-green. Push too far with harsh cleaners and you creep toward yellow, sometimes briefly before the color fades, because strong bases can damage the pigment. Keep it safe and calm. Work with kitchen acids and bases first. Use droppers. Keep bleach out of the party because it destroys the dye outright. And label everything you pour. Now turn this from a swatch test into living art that teaches. Paint a pale wash of cabbage purple over a page and let it dry. Sketch invisible lines with a cotton swab dipped in lemon juice and let them dry too. When you stroke over that area with fresh indicator, the hidden acid blooms in lettering you didn't show your audience beforehand. Reverse the trick on a second sheet using a swab in baking soda to make teal calligraphy appear in the purple field. For a performance piece you can narrate, paint a large petal in cabbage purple and load a fine brush with vinegar to shade the edges toward rose. Then feather the center with baking soda water to coax veins of turquoise that meet the rose and fade where the liquids mix. If you drip plain water along the boundary, the colors ease back toward violet and you've drawn a visible truce line. Neutralization as gradient rather than argument. For a real-time transformation, Pour a thin layer of purple indicator into a shallow dish and, with a pipette, add drops of baking soda solution at the corners and vinegar at the center. Blue-green ripples swim outward to meet crimson tides, and where they collide, delicate bruise purples appear. Now breathe through a straw at the blue-green corner and watch your breath. Rich in carbon dioxide, pull the color back toward pink as the gas dissolves, forms carbonic acid, and tips the balance. If you wait and stir, the dish drifts toward a single, calmer shade that reflects the average of your choices. You'll notice the paint feels different from watercolors. Some papers bleed and some hold crisp edges, because paper sizing and fiber density change how quickly the indicator soaks and how long you have before the color locks. Coffee filters and chromatography paper give sharp, honest transitions, while soft towels fuzz the borders. Heat also matters. Warm paper dries fast and freezes a moment. Cool paper gives you time to blend. A fan exaggerates the dry edge, while a humid room keeps gradients gentle. Extraction choices change the palette too. A quick hot water soak draws a balanced purple. A brief simmer deepens color but can dull the sensitivity, so keep it just below boil. A cold shake overnight yields a bright, lively extract that's sometimes truer to small changes. Blending with a splash of water and filtering through a coffee cone makes a strong stock that stores in the fridge for days. Freeze some in an ice tray and you have indicator cubes you can melt as needed without cooking new cabbage. If your colors disappoint, troubleshoot like a craftsperson rather than hoping. Gray or brown often means iron contamination from a pan. Switch to glass or stainless steel. Flat, unresponsive purple suggests your solutions are too weak. Concentrate the extract or your acid's bases. Blotchy patches usually come from oily fingerprints, handle paper by the edges. Fading under strong lights is real. Anthocyanins are light sensitive, so shoot photos early or spray a fixative meant for water-based inks if you want to keep a piece. Test first. Some sprays are mildly basic and will shift hues. You can build a pocket calibration without math. Prepare a ladder of known kitchen samples: white vinegar, more sour, vinegar diluted 1.1 with water, club soda, tap water, baking soda water, a level teaspoon in a cup, and a little stronger baking soda water, and stroke a line of indicator across a label card. Beneath each square write the name, dry the card, and you've made a reference you can hold to future pieces to read a color at a glance. Add a strip marked window cleaner or ammonia and circle it in red as a safety reminder. Once you trust the palette, explore subtle chemistry that looks like theater. Paint a row of identical purple squares. Then dust a fingertip with vitamin C powder and tap one square. Antioxidants can shift the dye toward warmer notes and sometimes mute blue-greens. Sprinkle a grain of salt on another. Salt alone won't swing pH much, but it changes wetting and can create halos as crystals dissolve. Dab club soda on a third. Watch it pink, then leave it on a warm windowsill. Pink will fade toward purple as the soda loses carbon dioxide to the air. In another square, write with diluted milk of magnesia and see a soft teal appear, proof that antacids are basic. In a last square, touch a whisper of bleach with a toothpick and watch the color die. A sober reminder that some agents don't change pH, they unmake the painter. You can connect these lessons to living things without repeating old arguments. Hydrangea blossoms that turn blue in acidic soils and pink in basic soils aren't doing a children's trick. The plant uses metal ions whose availability shifts with pH, and its own anthocyanins partner with those ions to tilt color. Cranberries and blueberries carry anthocyanins too, which is why jams change hue when you add lemon. In your kitchen, red cabbage sauté goes dull green if you toss in baking soda to keep it bright. You've changed pH in the pan. And cooks rescue purple by adding a squeeze of acid at the table. If you crave measurement, dip white paper strips into your extract, dry them, and you've made home pH paper. Touch a dot of mystery liquid and watch, but remember the caveats. Strongly colored samples can stain and lie. Carbonated drinks must be fresh to read sour, and buffers, like cola blended with milk, can hold one color longer than your hasty mix suggests. Keep the space safe. No strong acids or lye. Avoid mixing cleaners. Ventilate if you test household ammonia. Wear gloves when curiosity tempts you toward anything beyond food grade. And never taste laboratory cups even if they once held soup. Label bottles. Purple looks like juice. End with a small piece that slows the mind. Paint a horizon in cabbage violet. Let it dry. Load 2 brushes, one with lemon, one with baking soda water. Feather sunset pink into the sky from above, and sea green into the water from below until they almost touch. Then, with a clean wet brush, blend along the line until a soft grey-purple band forms. A truce not because you forced it, but because enough of each side met to cancel. As the paper dries, some areas will drift back toward one camp or the other, depending on where evaporation left more of one ingredient behind. And you'll see in colour what the numbers in tables only hint at. Acids and bases aren't enemies. They are partners that define a spectrum, and small changes in environment, air, heat, dilution, time, steer living colour the way quiet choices steer a day. Put the brush down and look at your hands. You made a painting that measures, a map of invisible balance that you can read later, an honest piece born from a vegetable. And now, when a recipe calls a sauce flat, or a pool strip shows the wrong shade, or a garden blooms an unexpected blue, you have more than a label. You have a felt sense for how the world's flavors and colors depend on where they sit along that shifting line, and how a drop here or there can rewrite the scene. Cornstarch Cymatics. Non-Newtonian standing shapes. Set a shallow puddle of cornstarch slurry on a tightly stretched membrane over a speaker. Touch play on a low note and wait. First comes a nervous shiver across the pale surface, then a tidy quilt of dimples, and when you nudge the volume past a shy threshold, the liquid grows spires and crawling fingers that stand where a fluid ought to flatten. A small stage where vibration and a mischievous kind of viscosity conspire to hold shapes in mid-quiver. You are watching cymatics in a suspension that refuses to behave like ordinary water, and the difference is what makes the show. Periodic shaking pushes the surface toward a standing wave pattern, and this particular mixture thickens abruptly under rapid shear. So the peaks and rims harden just enough, just long enough to resist collapse between beats, letting structures persist that would normally smear away. You don't need equations to feel the recipe, only care with setup because the most arresting forms arrive when simple choices line up. Make the slurry by sprinkling cornstarch into water, while stirring until it pours like heavy cream. Then add small pinches until a spoon dragged fast meets firm resistance, while a slow lift leaves a glossy ribbon. Aim for a thin layer, about the thickness of 2 or 3 coins, spread in a lightweight tray that sits on the speaker cone, or, better, on a sealed membrane taped to the cone, so no liquid finds your electronics. A square of food wrap or a silicone sheet keeps the driver safe, and a shallow plastic lid or pie tin on top of that turns the vibration into an even shake. Keep volumes modest and ears protected. You want clean motion, not thunder. Sweep slowly from say 20 to 80 Hz, and pay attention to 3 thresholds. First, the surface wakes into gentle ripples. Next, distinct standing patterns lock in, a honeycomb or checkerboard that holds for seconds at a time. Finally, with a notch more amplitude, lobes inflate into crisp plateaus and slender fingers rise, tilt, and march across the tray like curious animals. This is where the suspension's odd personality steps forward, lending solidity at the very moments of fastest motion. If you film with a phone and set the frame rate to match half the driving frequency, the shapes seem to freeze and breathe, a clue to what's really happening. The classic surface instability under vertical vibration prefers to oscillate at half the driving rate, so the texture you see is a subharmonic standing wave riding your steady beat, and the slurry's sheer thickening locks parts of that wave into stiffened ridges at the peaks of motion, before relaxing on the troughs. Small changes matter. A cooler, slightly thicker mixture writes sharper lattices and more stubborn spires. A warmer, looser slurry favors broad, soft hills that break sooner. A deeper pool damps high spots because the energy spends itself stirring bulk rather than sculpting the skin. A tray with smooth, symmetric edges encourages tidy, centered patterns, while a dent or ridge seeds asymmetry and births traveling defects that drift like slow comets. If dye or cocoa powder dusts the top, you'll watch pigment skitter toward the moving rims and sketch the currents that carry mass around each little hill. Boundaries decide the gallery. In a circular tin, you'll often see concentric rings give way to polygonal mosaics as you climb in frequency. In a rectangular tray, nodes align with the sides, and you get grids that tilt when you nudge the pitch. If you touch the rim lightly with a cotton swab, you can pin a node, anchoring the pattern like a fingertip on a guitar string and revealing how a single constraint reorganizes the whole scene. To understand why peaks don't collapse between beats, consider what the slurry is doing on the scale of grains. At small, slow deformations, water separates and lubricates the starch particles, and the mixture flows at fast, strong shearing, exactly what the rim of a rising hump feels each cycle. Particles crowd, jam, and create force chains that transmit stress like the struts of a tiny scaffold. The scaffold isn't permanent, but it needn't be. It only needs to outlast part of the cycle, giving the peak time to grow before the next shake renews the lattice. That dynamic jamming is why turning the volume up can, paradoxically, stabilize a shape, while turning it a hair down makes the same shape sag back into a ripple. You can test the idea without jargon. Lower the amplitude until the plateaus just begin to melt and you'll see the pattern blur. Nudge it up and the blur snaps back into crisp cells. Add a teaspoon of extra water and the spires shorten. Add a pinch of cornstarch and the same frequency-volume pair that once made dimples now raises a crown. Pause the tone and give the tray a gentle tap. The hardened rims slump and the surface evens in a breath. Proof that the solid was a momentary pact kept in motion. Frequency feels like a focus knob rather than a throttle. Lower notes favor larger cells. Higher notes carve finer mosaics. And overlaying two nearby tones makes moire fields that breathe and trade places as beating between frequencies waxes and wanes. If you sweep too fast, you'll miss the lock-in points where patterns clarify. So linger and let the suspension choose the mode it likes. Filming reveals behaviors your eyes might skip. A high shutter speed catches micro droplets that vault from the rim and rain back onto the troughs. A raking light thrown across the tray makes shadows that emphasize height and shows thin filaments connecting adjacent peaks just before they split. Slow motion captures walkers, localized lumps that orbit at the rim and hop a little each cycle, without the silicon oil mystique of other lab legends. If you brighten the dye and stand safely back, you'll see the edges of a plateau flicker as the jammed front forms and dissolves, a heartbeat for each little mesa. Keep the kit honest and kind to your gear. Protect the driver from moisture and grit. Never run tones that make the cone bottom out, and keep duration short, minutes, not hours, so heat and fatigue don't ruin a speaker. Place the tray in a secondary spill pan. Use gloves if you share tools for food. And when you're done, scrape the slurry into the trash and wipe with a damp rag. Never flush starch down a drain that you hope to keep. If nothing interesting appears, the mixture is usually to blame. Too thin, too deep, or full of bubbles that sap the clean snap you need. So stir. Rest a minute to relax foam, adjust with small additions, and try again at a slightly different frequency. If the tray skates, you're driving too hard or sitting on a slippery surface, pad the base with a foam ring to hold position. If the patterns shred into chaos, your tone is dirty or the container flexes, switch to a stiffer pan and a cleaner sign. The surprising part is how much you can learn about pattern selection and material response without a single symbol. You'll feel that systems often have sharp thresholds where structure appears. That resonance with the container matters as much as power, and that a material's behavior can flip with tempo. Soft under patience, reliable under excitement, yielding forms that last only because you keep asking the question on time. Outside your tray, cousins of this effect earn their keep. Industrial shakers settle slurries, tablet coaters stabilize bands of liquid on pills, and process engineers design around jamming fronts to avoid clogging lines. Inside the lab, researchers exploit these instabilities to mix gently at small scales, or to measure how suspensions transition from flow to jam under oscillatory stress. Even art schools borrow the stage to perform living textures for projection. knowing that the palette is not only color, but behavior. As the tone fades and the surface relaxes to a calm, glossy sheet, you're left with an intuition that stays useful beyond spectacle. Rhythm can create form where none would stand still, and properties that hide under steady hands reveal themselves when you keep time. You didn't force the slurry into statues. You offered periodic encouragement and let its own preferences write a relief map that existed only while you kept the beat. And sometimes that's the way to coax structure from a system, not by pressing harder, but by nudging in sync until the liquid remembers how to stand. Lyserjuice sand pendulum. Draw with resonance. Hang a small funnel filled with dry, sifted sand from a quiet frame so it can swing freely above a smooth board. Pinch the funnel's tip until a thin stream just whispers out, and give the bob one gentle push at a slight angle. Not a shove, more of a suggestion. And the floor becomes a notebook for motion. The sand stitches loops that braid and open. The lines tighten and then broaden as the swing slows. And a shape emerges that looks deliberate, though no hand guided it. You've built a lysergious sand pendulum, a drawing tool that turns resonance into ink. And the secret is that the bob is moving in two directions at once. One forward back and one side side, each with its own natural tempo. So the path your eye sees is the combined story of those two rhythms meeting in real time. You don't need math to feel how the choices decide the picture. Length sets tempo, angle sets attitude, timing sets the relationship, and every tweak writes a new sentence. Start with a stable frame, a ceiling hook anchored into a joist or a tripod that doesn't wobble. Hang the funnel from two thin cords attached to a small ring so the bob can swing both ways with almost no friction. If you want purer shapes, cross-suspend. Two separate cords at right angles meet at the ring, each with its own length. Because a pendulum's period depends mostly on its length, those two lengths become your pair of pitches, and ratios are everything. Equal lengths, equal tempos, give circles and ellipses depending on how you release. Shorten one chord a little so its swing is faster, and the figure becomes a figure 8 that closes neatly after a few cycles. Pick simple ratios like 2:1 or 3:2, and you get rosettes that repeat with poise. Pick messy ratios, and the line wanders the whole field, filling space like a thoughtful animal exploring a room. You can tune without symbols. Time 10 swings in one direction with a phone stopwatch. Adjust a knot up or down a centimeter and time again. You'll feel how small changes bend the drawing much more than brute force ever could. Phase, the when of each direction, makes the difference between a calm almond and a dramatic bow tie. Release the bob from a corner where both motions start together, and you'll get symmetrical loops. Hold the bob a hair to the side and let it go when one direction is already moving and you draw a curve that leans. You can even delay one axis by nudging the bob gently sideways a heartbeat after the main release, and the sand will record that tiny decision across the whole sheet as a twist in the loops. Damping is not your enemy here, it's your calligrapher. Because the swing slows with time, the line naturally drifts inward, and the figure tightens from wide arcs to delicate inner lace. You can emphasize that graceful fade by setting the funnel to leak a little less. So the final strokes are fine, or open it a touch for bold outer strokes that announce the pattern from across the room. Use play sand or fine table salt run through a sieve. Clumping sands leave stutters in the line. Dry the fill in a low oven if the room is humid, because moisture makes the stream cough and breaks curves into dots. Adjust the tip with a short piece of heat shrink tubing or a tiny clip so the stream is steady and thin. Hold the board level. Check with a bubble level or a smartphone app, because a slope tugs the whole drawing downhill and lies about your ratios. Safety is simple. Secure the mount above your head, keep fingers clear of the path, and collect sand on a big sheet for cleanup. Heavy bobs are not necessary. Mass mostly lengthens the swing. It doesn't make nicer art, so keep it light and kind to whatever it might bump. Once you trust the basics, you can let resonance do more than decorate. Gently tap the frame at a regular beat while the pendulum glides, and you'll see the loops swell when your taps match the bob's own timing and shrink when they're out of step. Resonance is the system, saying yes to small, well-timed pushes, and the page records the yes as balloons in the loops. Keep the taps steady for a dozen cycles and then stop, and you'll see where you were in step. The the swell, and where you fell behind, the pinch. A body-level lesson in why bridges walk under footsteps and why instrument makers care about how a table vibrates. If your frame can rotate slowly, a lazy Susan under the bass, turned by hand once in a while, the whole figure precesses and spirals appear, as if time itself were twisting the page. The motion isn't pretending to be a Foucault pendulum, but it lets you feel how a steady, slow turn gently shifts the meaning of a repeating stroke, the way seasons tilt the light on a familiar street. For an eye and hand calibration you can keep, run 3 drawings in a row, first with equal lengths, second with one chord shortened a finger's width, third with that chord shortened 2 fingers' widths. Label them and compare, same release, different ratios, and you'll learn to read the number of lobes along an axis as a count of how many times one direction completes a swing while the other finishes another. A kitchen version of how old harmonographs were read in parlors a century ago. Troubleshooting is part of the lesson and reveals real physics rather than scolding. If the line scribbles nervously, your pivot ring is catching or your chords twist. Polish the ring, add a tiny swivel, and reset the chords so they don't rub. If the figure slowly rotates when you didn't mean to, your bass isn't level or the chords aren't equal in stiffness. Swap one, and the rotation will vanish. If the sand sputters, the tip is too wide or damp, or the funnel is too full. Reduce the fill so the stream isn't forced. If the drawing looks lopsided though your lengths match, your release was off-center. Lift again, take a breath, and release from a steady spot. If nothing closes neatly, your ratio is far from simple. Enjoy the moiré, then nudge a knot and watch the figure snap into a repeating family. You can color without gimmicks. Layer salt tinted with a drop of food coloring in the funnel so the line subtly shifts hue as the swing decays. Or run 2 brief passes, the second at a slightly different ratio and a different color, to weave patterns that cross like voices in a duet. Want the physics to step forward without breaking the mood? Tape a tiny washer near one chord's top to change its effective length by the smallest amount, and see how a delicate shift at the support becomes a bold difference on the page. Place a strip of felt under one axis so friction is stronger in that direction, and the figure leans as if wind were in the room. Move the board a few centimeters mid-run, and you'll watch a clean discontinuity as the sand records your interruption. A literal edit mark you can point to when you explain that conditions write themselves into outcomes. The most human part arrives when you let the pendulum teach patience. Because the swing decays, the last inner loops often carry the clearest signature of your ratio. Because the stream can thin, the final strokes ask you to wait if you want them at all. Because the figure remembers how you released it, a quiet count to 3 before you let go yields calmer symmetry than a hasty drop. You begin to understand that control here is not grip, but preparation. Balance the lengths, level the field, choose a ratio, then step back and allow the object to speak its preference. That's resonance as a life skill. Get the timing right. Reduce friction at the pivot where choices hang, and small nudges will draw big, elegant curves. When the funnel empties and the bob settles, lift the page by its edges and tap loose grains back into the jar. Label the corner with your setup, equal lengths, slight phase delay, or 3.2 slow bass rotation, so your future self can read the figure like a diary entry. And as you stack the drawings, you'll see why these shapes have held attention since salon harmonographs and seaside pendula. They are mirrors that convert invisible rhythms into lines you can trace later with a fingertip. Proof that 2 simple motions, well prepared, weave complexity without confusion. Walk away with that felt sense more than any formula. When separate rhythms share a pivot and respect each other's timing, they don't cancel, they compose, and the page holds the music. Raw versus boiled egg spin. Inertia you can feel. Set 2 eggs on a smooth tabletop. One raw from the fridge, one that you've boiled and cooled, and give each a firm, flat-fingered spin as if you were sending a coin across felt. In seconds, you'll feel the difference in your palm and see it in the dance. The boiled egg snaps into a crisp whirl that glides, hums, and can even rise toward upright like a tiny top, while the raw egg wobbles, sighs, and slows, its shell jittering as if something inside were late to the meeting. That late is the whole lesson. When you spin an egg, you're not just moving a shell, you're negotiating with what's inside, and a liquid interior answers torque with delay, shear, and loss, whereas a set interior answers with unity. Start by noticing the boiled egg's confidence. It behaves almost like a rigid wooden ovoid because the white and yolk are coagulated and locked to the shell by friction. So when your fingers twist, the whole mass takes the same angular speed and keeps it, with only tiny losses to air drag and tabletop friction. The axis stabilizes because the shell and inside share a single plan. And if the surface is clean, you can coax the spinning boiled egg to stand up on its fat end. Friction at the contact point creates a horizontal torque. The egg's symmetry axis precesses toward vertical, and with energy still in the spin, the body chooses the orientation that best fits its rolling constraints. A pocket demonstration that tops stand, not because they want to climb, but because rotation couples to friction in a way that lifts the center of mass while reducing slip. Now watch its raw sibling. Inside, yolk and white are free and viscous, and the shell is only loosely coupled to them through a thin, sticky boundary layer, so your twist first accelerates the shell while the innards lag behind. A moment later, the liquid catches up and tugs back on the shell, stealing some speed and injecting wobble. Every millisecond, shear between layers warms the interior by a whisper, and you witness it as damping, useful when you want stability in machines, a liability when you want a pirouette in the kitchen. Try the classic stop and release test with both. Spin each egg, then, after a second, gently but decisively rest a fingertip on the shell to halt it, and lift your finger. The boiled egg stays nailed. The whole object lost angular momentum together. The raw egg, however, reawakens and creeps back into rotation, because the fluid inside was still turning, and friction at the inner shell slowly drags the shell along again. You can repeat at different speeds, and the signature never lies. Only the egg with a free interior resumes, a non-destructive truth serum before breakfast. Add a slow-motion video from your phone and you'll see deeper differences. The raw egg's apex scribes a lazy cone, its axis wandering, because the inner liquid keeps exchanging angular momentum with the shell. The boiled egg's axis draws a tighter cone that shrinks as friction bleeds energy away. A neat picture of damping in a nearly rigid body. Temperature and age let you tune the behavior within honest bounds. A colder raw egg is thicker inside. The albumin's viscosity rises, so it couples more strongly to the shell and spins better than a warm one, though it still won't match the boiled egg's crispness. An older raw egg holds a bigger air cell at the fat end as moisture escapes through the shell over days, shifting mass and altering wobble. You may notice the old raw egg settles more quickly or tilts oddly as that pocket sloshes and the yolk rides off center. Boil the same age egg and you stiffen whatever it's become, restoring unity even if the shifted mass distribution changes the way it stands up. You can get quantitative with kitchen tools without breaking the spell. Set a small tape flag on each shell, spin to a steady speed, and count revolutions before rest. The boiled egg outlasts the raw because it wastes less to internal shear. Weigh them before and after boiling, and you'll see a gram or two gone to steam loss. A tiny change that moves the center of mass a hair and can brighten the stand-up trick. Time 10 stop and release trials and average the re-spin angle for the raw egg. It will be consistent for that temperature, then decline as the egg warms and viscosity falls. If your boiled egg refuses to rise, likely the surface is too slick or the shell too damp. Wipe the spot, try a rougher board, and keep the spin strong, but not wild. If a boiled egg still behaves like a liquid, it's undercooked. Its interior didn't set enough to bind. If a raw egg seems weirdly solid from the fridge, give it a minute on the counter and try again. You're feeling temperature's hand. You can vary shape and see how geometry writes style. Quail eggs, more spherical, rise differently and precess less. A long goose egg is dramatic. It stand a slow climb if you get the speed right. Paint a tiny dot near each egg's fat end, and you'll watch the rising move in sync with that end finding the floor, a visual cue that the gyroscopic lift prefers a wider base. For a quiet extension, lay each egg on its side and nudge it gently, then stop it and release. Now try with a half-filled plastic capsule instead of an egg. The capsule mimics the raw case perfectly. It respins because the inner mass keeps going, an echo you can feel without protein or heat. Keep the experiment safe and honest. Spin on a cloth over a tray so an adventurous egg doesn't launch. Wash hands after handling raw eggs, and don't chase stand-ups on countertops that share space with heavy mugs. The reflection you take away is more than a party test for Sunday brunch. It's a bodily grasp of inertia, as something a system can either share or fight over. When parts are locked, a push becomes a single promise, and the motion is clean. When parts are free, pushes turn into negotiations and energy leaks into heat and sway. You learn that lag is not laziness, but a property, viscosity delaying consent, and that sometimes making something behave better is as simple as binding it to itself. You learn that rotation, friction, and shape can pull a body upright without any mystery beyond timing. And you learn to read hidden interiors from surface behavior. The one that spins back after you stop it carries motion inside. The one that doesn't has already told you everything. When you return both eggs to the carton, one marked for breakfast, the other for die or deviled plans, the tabletop feels a shade less ordinary. You can feel in your wrist what equations say in symbols. That motion likes to keep going. That how a system holds itself together decides how well it honors that urge. And that small rituals, like a spin and a touch, can make an invisible difference plain. Balancing forks on a toothpick. Center of mass magic. Hook two identical forks into the sides of a cork or a wad of modeling clay. Wedge a toothpick into the cork so it sticks straight out like a beak, and then rest the very tip of that toothpick on the lip of a glass. Suddenly the whole assembly hangs in mid-air, calm as a roosting bird, the forks leaning downward in a wide V while the toothpick's tip barely kisses the edge. It feels like a dare to gravity until you breathe and look closer. You didn't beat gravity. You negotiated with it by placing the system's center of mass below the support point, so any tiny nudge creates a restoring twist that steers the object back toward balance. And once you can feel that geometry in your hands, you start seeing balance not as a miracle of stillness, but as a conversation among weight, leverage, and where the average location of mass actually lives. Begin with the build that tells the truth without hidden tricks. Press the fork's handles into the cork on opposite sides, tines facing forward, handles crossing slightly behind the cork like wings folding in. Push the toothpick through the cork so that one end juts out cleanly between the fork handles. Now search for the sweet spot along the glass rim where the toothpick's tip rests and the forks settle into a symmetric bow. If the assembly slips, rotate the cork a few degrees, or slide the toothpick in and out to shift where the combined mass hangs, because the position of that center, a single point where you can imagine, all the weight acting moves as you move parts. The key sensation arrives when you tap the forks lightly. The structure dips and returns, as if tethered to the rim by an invisible spring. And that springiness is torque being your friend. Tilt the assembly, and gravity pulls the heavy mass back underneath the support point, exactly the way a pendulum under a pivot wants to swing back to the lowest place. That is why an arrangement that looks precarious is in fact forgiving. Small errors in where you place the toothpick or how you angle the forks are self-correcting as long as the center of mass sits below the contact, because any tilt increases the sideways component of gravity in a direction that pushes you home. If you try the same with a single fork impaled on a toothpick, you'll usually fail. The mass sits above the pivot, and a nudge sends it farther off because the torque now drives it away from level. The difference between returns to center and runs from center is just where that invisible point ends up relative to your support. Friction plays only a minor, clarifying role here. The toothpick's fine tip and the glass's clean edge make a tiny contact patch that prevents sliding, but doesn't hold you upright. Stability is born from geometry, not stickiness, which you can prove by balancing on a shiny spoon's edge or on a coin's rim. If the center still sits under the tip, the sculpture survives. Try variants that teach your fingers faster than words. Replace the cork with a gummy candy and push the toothpick at different angles. The best balance occurs where the combined center sits just a little below the rim, not far below. Too low and the forks hang so steeply that small vibrations become dramatic swings. Too high and the system turns nervous. Just below gives a gentle, slow correction you can feel if you breathe on it. Slide a coin onto one fork tip and watch the whole object roll and search for a new resting place. The coin shifts the center sideways, so you must adjust the toothpick's depth or rotate the assembly to recapture symmetry. A living diagram of how cranes and reach forklifts counterweight their long arms. Move the glass toward the table's edge and dare yourself to place the toothpick so only air lies beneath it. If the center remains on the room side of the rim, the shape hangs over empty space unfazed, because gravity cares where the weight is, not what your eyes think is scary. Pull the system too far and you cross a cliff. The line from the center to the earth no longer falls through the foot of support, and down you go. For a crowd pleaser that still tells an honest story, wet the toothpick's tip and press it to the glass, then light the far end of the toothpick and let it burn inward. As the glowing line nears the rim, blow it out. The ash crumbles. The support point subtly shifts upward into the char, and the sculpture stays put because the center of mass hasn't moved above the new contact. Nothing magic. You watch the fulcrum move while the weight stayed hanging underneath, and the standard of stability, center below support, remained true through the transition. You can measure without math if you want to catch the idea in a photograph. Hold a piece of thread from the fork's lowest point and let it dangle. The line of the thread points straight through the center of mass. Now note where that line crosses the toothpick's tip, relative to the glass. If the line passes inside the rim, you're safe. If it points outside, no amount of hoping saves the balance. Material choice clarifies subtleties. Heavier forks widen the basin of stability because the mass sits farther below the rim and the correcting torque grows. Very light plastic forks make a twitchy sculpture that is still stable but easy to disturb. A toothpick with a rough cut grips better, but too much friction hides your errors rather than curing them. The sweet build glides a little when wrong and settles when right, teaching your hands to trust the restoring torque rather than sticky contact. Even the shape of the rim writes its signature into the lesson. A thin, sharp edge lowers the effective pivot and increases the restoring arm, while a thick, rounded rim shifts the pivot upward. You'll feel the difference as either tenderness or stubbornness when you nudge the forks and watch how far the sculpture swings before it returns. If you want a controlled demonstration of why below is better, tape a small washer to the top of the cork so the added weight sits above the toothpick. Rebuild the balance carefully. Now tap. The swing grows anxious and the return weakens, often failing entirely if you add too much. Remove the washer, tap again, and serenity returns. The same geometry explains why tightrope walkers use long poles. The pole spreads mass outward and slightly below the wire, lowering the combined center and increasing rotational inertia so wobbles slow down, giving time to correct. Keep the table honest and your fingers safe. No open flames near polished wood. No balancing over glass that might tip. No fork points at eye level, and treat the cleanup as part of the ritual. The calmer your workspace, the more clearly you'll feel what changed when the center moved. For deeper curiosity, try what-if builds that isolate one idea at a time. What if you raise the pivot by stacking 2 coins under the toothpick? The same configuration suddenly teeters or fails because you've placed the support above the center. What if you switch the cork for a longer dowel so the toothpick protrudes farther? You've increased the lever arm for the restoring torque slightly and made placement touchier, but once found, very firm. What if you rotate the forks so their tines interlock more deeply? You concentrate mass closer to the center and must push the toothpick farther in to hang the center below the rim, like marching inward on a seesaw to keep balance when a friend walks closer. Troubleshoot like a practitioner rather than a magician. If the piece almost balances, then slides off, polish the idea, not the glass. Reseat the toothpick so the center falls inside the rim. If it balances but shivers, reduce drafts, lower the assembly's height by switching to shorter forks or a shallower glass, or widen the fork angle to drop the center a touch. If it refuses all invitations, check symmetry. Identical forks, equal insertion depth. toothpick centered in the cork. Small asymmetries move the center sideways more than you expect. And when the sculpture finally pauses and becomes quiet, notice the invitation it leaves behind. You now own a physical sense for center of mass and torque that outlives the tabletop. Why backpacks ride close to the spine. Why a low-slung camera rig feels gentle on a shoulder. Why a child on a swing slows when they tuck and speeds the sway when they extend. Why a loaded truck takes curves differently when the cargo is strapped low versus stacked high. The forks on a toothpick are not a party trick so much as a pocket apprenticeship. You learn to look past surfaces to where the weight actually lives, to aim that invisible point under your support, and to trust that when design makes the down pull, create a back-to-center twist, stability is no longer fragile, it's earned. When you finally lift the assembly and scatter the pieces back into the drawer, the rim of the glass seems changed. You know that its narrow edge can hold a small world if you place that world's heart in the right place. And you leave with a quiet habit. Before you balance anything, an object, a schedule, a decision, ask where the center really is, and whether you've put your pivot where gravity will help you instead of argue.